new ideas for a new second-generation time-sharing system. And GE submitted a proposal. They ended up winning. And that ended up becoming an operating system called Multics. And then some of the guys, after that project was finished, went to AT&T, and they created something called Unix. And then a bunch of other important things happened, and then we're here. So I'm done. Another little organization called IBM also submitted a proposal for the next generation time-sharing system, and they submitted a batch operating system idea. Apparently they didn't get the memo that this was supposed to be a time-sharing system. So they didn't win, and they were very surprised by this. So stinging from their defeat, they regrouped and decided to approach the idea of multiple people running programs on a computer at the same time. They decided, well, we like this batch operating system kind of thing. We like this running one program on the machine at the time. We make it so that one person can run a program on a machine, but have multiple machines in the machine. And that's how virtualization was born. They didn't call it virtualization. They didn't call it virtual machines. They used the word guest and the word host, which was new and interesting. So they came up with this project, which ended up being called CP40, CP for Control Program. That was the word they used for what we would now call a hypervisor. They came up with the word hypervisor later on. CP40 used a Model 40 System 360 mainframe to do that. There was only one of those ever. It was just a research project, but it was successful enough that they productized it into CP67. And so that was the running on it. So this was for the CTS IBM 7094, and this was a 360 mainframe, part of it. And then CP67, it evolved over time to become VM370, VMCMS, and other mainframe virtualization products. But that's where all this stuff came from. Now, along the way, IBM wasn't the only group thinking about virtualization. There were various research projects going on, research scientists working on this concept. And in 1974, two professors, Popek and Goldberg, wrote a paper. It was published in the Communications of the ACM in 1974. And they came up with what I call they didn't call them laws because they weren't really. It's just a little inside joke. And as with those first three, I then laid two more to make the three laws. There's resource control and efficiency equivalence, meaning that they realized that in order to have effective virtual, a program had to run the same in a virtual machine as it would on bare metal. And that was a new concept at the time. We sort of take it for granted now. But that was the concept of equivalence. If you're going to put multiple people on a machine, especially if they think they have the whole machine to themselves, then you need resource controls to make sure that one person doesn't hog all the physical resources of the machine, take up all the CPU time, all the RAM, to allow everyone to make forward progress with their software. And efficiency, they said that the dominant portion of processing of a program has to run at roughly the same speed it would on bare metal, or the same speed on bare metal. They realized that there are going to be with virtualization, but they use that phrase, the dominant portion. Now, back in those days, especially in the days of batch operating systems, security was the door and the key to the door, because as long as you could keep people out of the room that had the computer in it, then you had a secure machine. Now we have this nifty thing called the internet, so security is a big issue, so it's an issue for virtualization. And lastly, the least administrative observability. This is required. This is a nice to have concept. So that from one central place, you can look into all of the workloads in all of the virtual environments to see what's going on in them. This is very hard to do with virtual machines. This is not that hard to do with containers. So this is one of those advantages that containers have over virtual machines, that ability to look into the processes. So if you're responsible for the whole machine and there's a problem, a performance problem or other, then it's nice to be able to look into what everyone's doing to see what's going on and who's causing the problem. So that nice introduction then led to what I call the dark ages, where not much happened. This was a time period when most of the computing industry was focused on two things: clock rate, increasing clock rate as much as possible, and making systems as small and as cheap as possible. And so some companies that I won't name for obvious reasons really went with the one person per computer model. And did a good job with it. They were very, very successful with that, that's a good thing. But in the meantime, in here, not much happened with regards to virtualization. Somebody thought of this concept of a virtual file system tree that would be part of the whole tree, and they called that a trooted environment. That was created for Unix version in around 1979. That was then ported to other versions of Unix, and Bill Joy ported it to BSD4, which then became more widespread that way. 1991, somebody just used the word jail to refer to one of these things, and from that, someone came up with the word jailbreak. But nothing new there. Java Virtual Machine, the first that I know of, the first virtual machine that didn't have an analog in the physical world. So it wasn't, let's virtualize an existing machine, let's virtualize something that doesn't even exist. And then something which many people would not call virtualization, but partitioning, Sun's dynamic domains. That was take a big computer and isolate it down to the power grid. Isolate some of the physical resources, some of the CPUs, some of the RAM, some of the I/O cards, make that a domain with a copy of an operating system running on it that was completely isolated from the others, so that if anything bad happened in here, it wouldn't affect the others. So partitioning has some strengths there in that level of isolation. And with the dynamic domains, you could even shift the border back and forth between the boards to grow a running domain while it was still in production and shrink some other ones. But that was about it for that 25-year period. So let's talk a little bit more about the different kinds of virtualization. I've been using this I keep modifying it, but I've been using this for almost a decade now to discuss those kinds of virtualization. Over on the left-hand side, partitioning, where you have the best isolation. You have more isolation as you go farther that way, but the least flexibility. If you want a program to use a little bit more CPU power, and you have those partitions, you can't do that. You can't give it a little more power. Over on the right, we have containers, more flexibility, but less isolation. And in the middle, you have those virtual machines that use a hypervisor. So here, you can see in this diagram the partitioning and the separate physical resources with virtual machines. There's different features with the different implementations, but you always have a hypervisor, and virtual machines that are these fictional constructs, pretend computers. And on the right-hand side, OS virtualization, containers, where you have one operating system instance and multiple virtual operating systems inside. Most flexibility here because at any time, the operating system can give just a little bit more of some resource to a process up here that needs it. And you can consider these as just a set of processes that have some shared characteristics. So very flexible in software. Of course, the advantage is over here, like I said, if any one of these fails, the rest of them keep running. Here, if one of these crashes for some reason, it doesn't affect the others, but if the hypervisor crashes, then all of the guests are going to come down with it, which is similar to here. If the operating system fails, all of the guests come down with it. So if you're configuring for high availability, you need to take the different availability characteristics of these models into consideration to get to the level of availability that you want. way ahead. Good. So that leads me finally to a definition. As I mentioned, a container or zone is a collection of software processes unified by one namespace. So that's one Etsy hosts file, one Etsy password file, one set of printers, one DNS, LDAP. All these naming systems unify all the processes in one container, but can be different in another container. This is, I'm of course speaking generally. Implementation of containers might do things a little bit differently. You might have one unified namespace. I would call that less of a container. But they all share access to one kernel. So all of them are making system calls into that one kernel. So the kernel has to do this stuff and know what to allow and what to forbid. So the kernel has to know this process is allowed to use this device, but this other process is not. Implementations of containers distinguish them from each other. Usually, the rule is two containers should not be able to communicate directly in a way that two machines wouldn't be able to communicate. So they should still be using network semantics to talk to each other and not have some covert channel that is different, because that usually leads to security issues. And that goes back to that fourth of the 5.3 laws. So some of the advantages of containers: typically they leverage a mature operating system. So Solaris, Linux, many operating systems that have been around for a decade or more, the features that are in there can easily be leveraged in an implementation of containers. Virtual machines, containers are very lightweight. So a virtual machine is going to have its own kernel, which is going to take up RAM. It's going to take up other resources. Containers don't have that. They all share that kernel, so you just saved some RAM right there. Because you don't have to boot a full kernel when you're booting a container, containers typically boot very quickly. And they can boot in just a few seconds, because all it is starting up a few processes. And that's easy to do. Containers are machines where the hypervisor usually is software running on a CPU. That takes up CPU time. That CPU time is a workload. So hypervisor right there creates performance overhead. Hypervisors also have to usually get involved with any I/O, because if you only have a couple of I/O cards, a network card and a fiber channel card, and you have a bunch of guests sharing those, the hypervisor has to make sure that the right guests are doing the right things across those I/O cards. So that's more time the hypervisor is spending on the CPU, using up CPU cycles. Also with virtual machines, the hypervisor has to go and flush the CPU caches to get all the data out of there. Next guest to run on that core can't access that data in cache. So there's more overhead. Containers don't have any of that. So there should be no overhead. I was part of a team this is back in 2008, part of a team within Sun. We were comparing the performance overhead of various virtualization technologies, and I did the performance characterization for zones. And we used CPU benchmark, network benchmark, storage benchmark, and some other composite benchmarks. And for every one of them, I found zero overhead for zones. And there shouldn't be. A process is exactly the same thing, instruction by instruction, as that process would perform running on bare metal. When it makes a system call into the kernel. The kernel takes care of that. So there's no extra links to the instruction code path. So there's no overhead. That's how it should be. Hypervisors started out very simple. CP40. It's a very simple hypervisor. Now they're much more complicated, much more feature rich. That's a good thing, but for most hypervisors, that's new code. They have generated unless they were able to take code from something else and use it in their hypervisor. Operating systems already had all these features, already had I/O, already had schedulers, already had efficient virtual memory systems. So containers take advantage of those features. Yeah. Everything that has advantages has disadvantages. And so these are some of the disadvantages of containers. Typically, and especially the first generation of a container implementation uses homogeneous operating systems. The container is the same OS as the underlying kernel. You can change that. You can create a translation layer that translates from the guest's system call layer, the top of that layer, to the kernel's system call layer. That's going to introduce some performance overhead, but you can do that. And for zones, we do that for different versions of Solaris. As I mentioned before, there's less isolation for containers. A problem with the kernel could affect multiple containers, but you can mitigate that with some features in the operating system, and of course with load balanced instances. And then, as opposed to the dark ages, everything happened. On top are all the operating system virtualization technologies that I could find. So on top, just as a reference point, I put all the virtual machine technologies in this time period on the bottom, or at least a good set of them. So this is where it all happened. 15, 16 years, this is when virtualization exploded. I'm not going to go through all of these because Kira's going to help me. So what we're going to do here is, we're not going to talk about the VM. This isn't VM days, this is container days. We are going to talk about the top above the line, and we have more time than we were supposed to have, so that's a good thing. So you don't have to talk so fast. We're going to split these up a little bit into, I had to come up with some arbitrary way of dividing them up in roughly half. So I came up with the distinction of the Unix ones versus the non-Unix ones. So Kira's going to come up and talk about the non-Unix ones first, and then I'll come back. I'll give you a break from my voice. I'll come back and talk more about the Unix ones and focus on one in particular. Kira's going to focus on one in particular for these. And then after we have these more or less deep dives, deep shallow dives, then we'll wrap up the whole session with some conversation about what's happening right now, what's the focus now, and what to expect from the future. So, Kira, switch here. Give us 1 minute. Oh, I can just pull it up right here. If you want, I can give you that. Or do you want yours?
I think, yeah, I'd rather mine. Just make some changes. This one?
Yeah, yes. Go ahead and plug it. Which one is that? Oh yeah, okay, upside down. You can use this one, or you can use that mic, whichever one you prefer.
Yeah.
With this one, you can walk around.
That's right.
This is Kevin. He runs the AV show. using Linux?
Yeah. I tried it. It was working.
Yeah, no, it's it'd be yeah, that's good. I think that worked. So let's try.
Yep. Yep. I just tested it. Oh, okay. Can you hear me? No? Oh. All right. Thanks to the organizers for inviting me all the way. I came all the way from Seattle to do a nested talk. I really like the idea of talk within a talk. What I don't like is I only have like 15 minutes, so let's get started. First of all, my affiliation. I was working for Parallels, and they recently rebranded themselves to Odin. So I work for and the projects I'm working on are mostly OpenVZ virtual containers, new checkpoint restoring user space for Linux. So you know my view is a bit skewed towards those. So for Linux, it all in 1999. Then our chief scientist got that idea that he was inspired by IBM mainframes that were able to do that partitioning Jeff was talking about, and he wanted to do the same inside the system, inside the Linux kernel, on a different level. The name of that at the time for us was virtual environments, VEs, as opposed to VMs. So basically the same idea, isolated groups of processes running on top of one single kernel. And the other idea was to have a special file system in order to share the code, the binaries and the libraries, and therefore share RAM between containers and make density higher. And the last idea was some resource management to keep the containers within the limits, the isolation basically. And in 2000, we had like 5 engineers working, and we made initial testing of our technology by putting a couple of servers. One was running those virtual environments, the other was running the web front end for those. And we got 5,000 of those VEs on that server at the time. And initial testing revealed that we have really huge resource isolation. So people were running bots, fork bombs, and whatnot, and we had to handle it somehow. So we hired a guy from Moscow State University, a mathematician. MSU is like Stanford here, I think. And this guy wrote a subsystem for Linux called user. This is basically per limits. So the problem with Unix and Linux at the time was that all the limits were per process. And in modern age, even a web server is not a process, it's a groups of processes. And containers are also groups of processes. So there was a need to get the per process group limits. And I think the idea was taken, the user being counters idea was taken from HPUX, and they had the so-called LUID, and with, I don't know what L means, basically a group of processes. So he wrote the first implementation of that. And at the same time, prolific Linux kernel contributor Alviro implemented the so-called namespace. And now we call it mount namespace. It's basically the same idea as chroot, just with some added bells and whistles, so you can do more with the mount namespace than with chroot. And at that time, it was just called namespace because there were no other namespaces. Later, we did more. So jumping into this century, the next 5 years, I call it Stone Age, we had that good experience with our idea. It worked. So some crazy people in our company decided to implement that for Windows as well. Of course, it's pretty crazy. There's no source code, and you have to basically reverse engineer everything and patch the kernel dynamically. And you even have to, in the Windows kernel, there's a patch guard that prevents the kernel from being modified, so it has to be hacked around, and this is what they did. And but yeah, they start working in 2001, and in 2004 they made a release. And this Virtuoso for Windows is still here. We do have that software, and we sell it. Also, in 2001, another Linux container project was started, and was called Linux vServer, and it's still here, and was started by Jacques Gelinas, and now it's run by Herbert Peltzel for the last 13 years, I guess. The only problem with Linux, they don't really want to back upstream into the upstream Linux, so it's totally off the mainline project. In 2000, released the first commercial Virtuoso, and we call it. And also, it's just what the thing. I forgot one project that was where, and it's called Meiosis Metacluster. That was some guys from France. What they did is they did live migration for all running on Linux. And for live migration, you need some sort of the container. It's a prerequisite for the live migration. So you don't want a process or groups of processes to disappear out of nowhere. So you make to have it a bit isolated, and this is why container is needed for live migration. So these guys, they have product for that they sold, and it was doing live migration. It was also containers, but just for the for live migration. And they were acquired by IBM in 2005, and I'm not sure, but I believe this team was working on making containers for IBM iX, WPARS, right? Workload partitions. The containers in iX was partition. So in 2004, there was also a project from IBM that's called CKRM, Resource Management Framework, and it was the same idea as user bean counters, basically per group process limits, per process group limits, various limits and guarantees. Unfortunately, this is a demonstration why most of the projects that are developed in-house and then released into public, they don't work. And failed with a few of such projects at that time. They also did enterprise logical volume management system that came out of nowhere and was not accepted into upstream, and then slowly died. And CKRM was another such project. It probably was engineered, but the main problem was that it just appeared out of nowhere. Kernel developers, they don't like things that way. And finally, in 2005, we realized we are also not doing the right thing by having the product closed source. So we have founded OpenVZ as a way to open source our containers technology. And the term container, I believe Jeff might know better, but the term container was appeared at about 2004 or so. I tried to trace it, and the first thing I found it definitely came from Sun, and I thought it's about 2004. So later we renamed our virtual environments into containers. And with the born of OpenVZ project, we started to put stuff upstream, and this is what my next slide is about. So this is the way the stuff is going upstream. Lots of container-related patches were contributed to the Linux kernel. And I'm told by the fact that our company, we have a kernel team of about 10 engineers, and with our upstreaming efforts, mostly for container-related technologies, we are made into top 10 companies that go to the Linux kernel. And the other guys there are way bigger, it's like you know, Red Hat, IBM, and guys like that. So yeah, upstreaming is probably as complicated for developers as this Salmon run. So to the right, you can see the developer trying to push this code upstream, and to the left, you can see a Linux kernel subsystem maintainer. But nevertheless, a lot of code got into. So there appeared a lot of new namespaces. But namespace is probably not the right term for that, because for file system, it's clear the files have names, so the files, it's a namespace. But for network, for example, the namespace is basically what comprises the network on the Linux server, on the host, on the computer. This is network cards, network interfaces, routing rules, firewall rules, and so on, various network caches and so on. So this is what network namespace is. Basically, when network namespace was merged, Linux got the ability to have isolated domain consisting of devices, routing rules, IP tables, and so on and so forth. That was a result of work of our developers, and they had to write it from scratch using our experience from Virtuoso, but rewriting the code from scratch in order for it to be accepted upstream. Same happened with the PID namespace. PID is process ID, and each container has its own tree of process with its own PIDs, and therefore there is a need for the separate domain, separate process IDs. And for PID namespace, I believe there were 3 implementations. One from us, another from IBM, and then yet another one from us. And that third one got through and was accepted into upstream. So these 2 are the biggest namespaces. IPC is Inter-Process Communication System 5 IPC that consists of shared memory, message queues, and semaphores. And then there is a user namespace, basically an ability to have all the file system and per process UIDs, user IDs, group IDs, and all of that. So in your own container, you have your own IDs. This namespace went in 2007, but it was only completed very recently in 2013. Also in 2006, we opened live migration for OpenVZ. That is a way to take the container from one host and move it to another without shutting it down, without stopping any processes inside. We're migrating all the TCP IP connections and so on. Live migration already existed for VMs, but from the point of view of the underlying thing, that is either a kernel or the hypervisor, VM is much more uniform, so it's way easier to live migrate a VM than to live migrate a container For container, we have to care about everything, like all the network buffers, all the running process, open descriptors, various caches. It's a lot of work. I think that at that time, live migration was like half the code of also another attempt for process group-based management from Google, and unlike IBM, this approach went through. What Google guys did is they take the feature called CPU sets that were used to assign pools of CPUs to pools of processes, and they generalized it. So there was an ability to group the processes, make some process group, hierarchical maybe, and apply some resource controllers to those groups. First, resource control was CPU sets, and then they appear like controllers for I/O limits, memory controllers, like some pretty simple controllers like limit for number of processes in that group, and so on. This is pretty much the same as our user bin counters. It's just unlike user bin counters, C groups made their way to the upstream kernel. So we're switching to that now. Also, all this stuff appeared in the Linux kernel, and therefore LXC tool appeared to make advantage of this new technology. So contrary to what most people think, LXC is not Linux containers. LXC is just a user space tool to employ, to take advantage of those new features in the Linux kernel. I think that's pretty important. And LXC is a tool from IBM. IBM was pretty involved with containers at the time. I don't think they are as involved as they were at the time. Contemporaneity. I had to look this term in the dictionary. Make myself look smarter. So the big part of all containers is resource management. And we had several approaches to that. First of our approach was user bin counters. It controlled everything. It was limiting containers from other containers to not step on each other's toes in terms of this. It was pretty good. The only problem was it was really hard to configure. 21 interdependent parameters that you should set for each of the containers. So we came with various ways, like written a book about those user bin counters. We've written a lot of tools to manage those user bin counter sets. We had sample configs and so on, but it wasn't working really well. Aside maybe for people who really read through that big book. So we came up with the second generation of resource management, and it was complete failure. It was simple, but it wasn't really. So this SWAP is the third generation resource management that we came up with. It's simple to configure, yet working. It's simple to configure because, as with real hardware or as with hypervisor, you only have two limits, RAM and swap. This is it. I mean, there are also CPU limits, but it's a separate subsystem. Also, in 2010, we came up with PLOOP. It's basically a container in a file technology, file system in a file, same as for VMs. Previously, we were using Truth, and we found out that multiple containers on the same file system is not a good idea because they share the common file system journal, because they share the common characteristics of that, because we had to add a per directory quotas to the. So we ended up that PLOOP technology, which is a file system in a file with some bells and whistles. In 2011, we came up with CREW. This is checkpoint and restore in user space. The problem, it's the same problem as we as was shown on my photo of grizzly bears and salmons, basically our in-kernel checkpoint restore is a very, very complex thing, and we tried it upstream to no avail because it was touching each and every subsystem with our code, and no that. Other guys were also trying to have to merge checkpoint restore in the Linux kernel, and they also failed. I know a guy who spent like 3 years of his life doing exactly that, trying to merge checkpoint restore to the Linux kernel, and we also failed. So circumvented the system by the checkpoint restore work in user space, with the kernel exporting some mechanisms for that. So for example, for the stuff that's happening to processes in Linux, you can get it from /proc. You can get some stuff about the processes by using some debug facilities like ptrace. You can get some stuff from inside the process itself, using all those mechanisms and more to get the image of the running processes and save it in the file. And we use some other mechanisms to restore that later. So this is a prerequisite to the live migration. Checkpoint the processes and then restore it on the different machines. Also, during that time, 2 years ago, plenty of new container projects appears. Of that, I would like to mention Docker, CoreOS, and Google LM. So let me contain that for you. That's the name. In 2014, we got for Docker and LXC, and I think it's just recently that Docker merged our support for Creo, so you can now Docker checkpoint and Docker restore. And finally, just we realized that we are doing OpenVZ all wrong. It's open source, but the process itself is closed source. So we doing a reborn of OpenVZ with new development model, with everything in public, with more code available, with more repositories. Our developers sitting in the same room, but they talking through the mailing list, through a public mailing list, which you can read and you can talk to them too. It's just a few words for the future. It's 15 years of history, but we're not done yet. That Virtuoso 4.7 is our future OpenVZ, what they're working on right now. And we actually invented yet another generation of resource management, this time with a user space daemon helping and adding our resource management will become more dynamic with bursts, guarantees over time. And we'll probably do proper port to Power and ARM architectures, because the improper port, I did that like 10 years ago just to, because the technology, containers technology, is architecture independent, and therefore it's very easy to port to various architectures, unlike VMs that require deep understanding of the architecture, CPU, and so on. So for Creo, we have a sub-project of Creo called P-hole. This is the project for live migration, because Creo doesn't care about live migration. It's only about checkpoint and restore. And with Creo, we want to integrate this into many, many different things. There are some other projects that we're working on. They maybe come through or not. I don't know. But I have a talk tomorrow, and I'll be talking about these things in more details tomorrow. This is as much as I can do. Thank you so much.
There it is. All right, last section. We're in the, where the point? There's in the home stretch here. History takes a long time. That's why they call it history. So a quick run through on the of containers in the Unix space, and then I'll talk about the application of those 5.3 laws to one of these. The one that I know best, apparently well enough to write part of the book. So it's, in the Unix space, this started off with FreeBSD jails back in 1999, 2000, somewhere in there. It's a good implementation of containers, provided isolation of processes, file system, a couple of other things, some administration delegation, but it was weak in some isolation, some areas of isolation, such as networking, a shared network stack for all of the, so good. Then 2005, Sun released Solaris Zones. That was I call it a very complete implementation with one section, one of those things missing, which we addressed 2 years later. So Solaris Zones had a complete separation of namespace per zone. So one its own root directory and all the files under /etc and all those things. Per zone users, per zone permissions, privileges. I'll talk more about those in a couple of slides. January 2005, that Sun released that. HPUX had the resource management piece as Solaris had. There was Solaris Resource Manager from a long time ago. HPUX had a similar resource manager called SRPs, Secure Resource Partitions, for resource management, but no namespace isolation. So they addressed that in around 2007 with HPUX SRP v2, which offered that namespace isolation. Closely followed by, and this is, I think this is where the containers word comes from, but I haven't found anything else to prove it. With Solaris, we merged this namespace part of zones and the resource manager features together to add that requirement of virtualization. We renamed that to be containers. And so you see Solaris containers. And that stayed around for quite a while. So in the book, we decided to stick with the phrase Solaris containers and not confuse people with Solaris zones, even though our marketing people would confuse them. So we used containers, and that stuck around until 2011. So that was after the acquisition of Sun. When we decided this using Solaris zones and Solaris containers, when it's basically the same thing, was just too confusing. So we dropped the word containers and stuck with the first term, Solaris zones. So it's kind of ironic there that we dropped it. 2008, IBM came out with AIX workload partitions, WPARs, basically a clone of zones. The features, they all line up. They did have some additional features that they had that Solaris zones didn't, which was good for them. HPUX then, 2011, in one of the 11i releases, one of the updates, they came out with namespace isolation to add to their secure resource partitions. And then they renamed that to be system containers. They also offered HP 9000 containers, which was kind of interesting. That's a HPUX container, but to run old previous architecture HP 9000 code, which required binary emulation, real time. And you can guess what happens to the performance when you do binary translation in real time. And then I put this here from containers. It's neither a container nor a virtual machine, so I put it straddling the line to indicate that with a little arrow. The kernel zone, I'll talk more about this later, but it's a kernel running in a container on top of the container for the kernel for the system, which offers some more flexibility.
So it's like the host kernel acts as a hypervisor?
So in some ways, and there's even a marketing thing which says that, but yes, the Solaris 11 kernel acts in some ways as a hypervisor. And so I have part of it below the line. Do that and define. So I thought it would be interesting to apply those original 5.3 laws to one technologies And the one that was easy for me to do was zones. So I'm going to take a few minutes and do that. So this is the same things as before, but applied. Equivalence. The program running, as I mentioned before, for performance overhead, the program running in a zone runs exactly the same as it does not. No difference at all. In fact, it's hard to tell that you're in a zone. We didn't try to hide it. It's not like that. But you have to know the couple of commands that will then give you the output that will essentially tell you, oh yeah, you're running in a zone. That's how transparent it is. Resource controls. The resource controls that came from Solaris Resource Manager. I'll talk a little bit more about those in another slide. As I mentioned before, there's no software layer between a process running in a zone and the kernel, so there's no performance overhead. Solaris 10 added to Solaris something called privileges. This is fine-grained privileges. In the old, well, in most Unixes and Unix things that are sort of like Unix in some way, there's this root user, and the root user can do anything. And that's good if there's a very small number of root users, but big companies that want accountability and need to give multiple people the ability to manage a machine, they want something in the log file that says something besides the root user logged in. Well, who is that? I need to know who to blame for what the FCC is coming after me for, or the SEC. So they asked us years ago to make this different, to get rid of the root user. So for Solaris 11, there is no root user. There's a root. So a person logs in, if given access of these privileges, can use those privileges to do very specific things. So you can have a normal user who has the ability to modify the system time clock and change it to an hour ago or an hour from now. But that's the only thing that the root user normally could do that user can do. And there's about 50 different privileges. And we went through the code and looked for all the places where it said, if UID equals 0, then allow this. Now it says, if this user has this privilege, then allow that.
All capabilities in Linux.
Sure. Yeah. So we did that with zones. And you can have any set of those privileges with the exception of a few that zones can't have. There's a default set, and you can increase that or decrease that. I'll talk a little bit more about that. And like I mentioned before, when you install Solaris, you have what's called the global zone. That's the normal Unix-like environment. And all the other zones are called non-global zones and some variations there. But from the global zone, a person with sufficient privileges can see into any of the processes in any of the zones. And it's very useful. So these are these 5 things that are core pieces of zones or containers. I have a very long blog that's been going on for many years. There's a lot of stuff about Solaris zones in there. So if you want, you can go check that out. So I mentioned those privileges, these fine-grained abilities. Here's the you to modify the system time clock. One that allows you to be an SMB server. You can create a zone that serves up files to Microsoft Windows clients out there on the network, or a zone that's the NFS server. You can have lots of these things. I booted 1,000 zones on an 8-core system about 6 years ago, and it was kind of interesting. That's also in my blog. So these privileges define the security boundary around a zone. By default, it's very safe, and we don't have any record of security issues with someone breaking out of a zone or into a zone. But you can tailor that. You can add privileges, so you can give a zone this privilege for the time clock and make that zone the only one that's able to modify the system time clock for all of the system and all the zones. That might be connected to the web and to some NTP server out there, the sense of time, and set it for the whole system. If you do that, you probably want to take away other privileges because that's a web-facing, directly connected to the web. This set of privileges is configurable, so you can change it later on if you want to, if you decide the security is or too tight. Also, to demonstrate the secureness of a zone, Back in the Solaris 8 days, 15 years ago, we had this version of Solaris 8 called Trusted Solaris 8, which set up data compartmentalization. The US government, intelligence agencies, Department of Defense, they need to have a computer that has the area where the secret data is and the top is and other classification labels that I'm not allowed to know about because I don't have a security clearance. And we used to do that with Trusted Solaris 8 in a certain way that was very, very finely tuned to move forward. So there was no Trusted Solaris 9. For Solaris 10, we used zones to do this. So a zone is a top secret zone. Another zone is the secret zone. Different levels of compartmentalization. And you can't even copy and paste on a workstation from one window that's top secret into another one that's only secret. It's not allowed by the kernel. So we do this for them. You trust the security of zones to separate that data. So that sounds to me like it's pretty secure. And if you have security needs that are greater than that, I don't want to know about it. Sure. Oh, thank you. All right, I'll be quick. Sorry about that. So as I mentioned in the beginning, namespace, we've gone over that quite a bit. Lots of file system choices for zones. So you can share data or have isolated data. You can make a zone read-only. So all the Solaris content itself cannot be modified, no matter what privileges you have in the zone. That prevents Trojan horses. In Solaris 11, we also added a bunch of network virtualization features. So we have virtual NICs, virtual switches, what are essentially virtual routers, but a virtual router is just a zone with two virtual NICs and routing turned on, and then you do whatever you want inside there. Which also has load balancing and NAT and firewall features. So you can create a zone that's a firewall. One side goes out, one side goes into all of your zones on the inside that themselves don't have any network connection to the outside. Even an elastic virtual switch, it's a layer 2 switch that spans multiple computers. And the different zones in the computers can connect to this switch, and they all think they're on the same switch, which has interesting availability characteristics. With all this, you can build any arbitrary network structure with IP addresses. You take a physical network and put it inside of a Solaris system with different zones for the different workloads. More security features like IP and MAC address spoof prevention. Lots of resources. I wish I had more time to talk about them, but partitioning of CPUs, accounting caps on CPU time. There's a fair share scheduler that's been in there for forever. RAM caps, VM caps, all these things part of resource management to make sure that one zone doesn't take over a system resources than it should. We also have what we call non-native zones. So those kernel zones I mentioned with a separate kernel level, separate patch level for that kernel. And the layer between them is very clean. So when Solaris 11.3 comes out, you can run a Solaris 11.3 kernel zone on top of a Solaris 11.2, which is sort of backwards in the compatibility context. You can run Solaris 10 zones in a Solaris 11 system, so old workloads can move forward and then still use the Solaris 11 features like network virtualization and transparent encryption. So that was way too fast, but I hope that helped understand some of the ways that you can implement those 5 3 laws. So what's happening now? The virtualization, creating virtualization has largely matured. We're still seeing some things come out, Microsoft containers, Windows containers, those sorts of things. But we are also moving forward into the next phase of virtualization. Okay, now I've got 1,000 Solaris zones on one Solaris system. How do I manage that? Managing 1,000 computers is hard. It's not all that much easier inside of one system. So we see things like Ops Center, which could manage both zones and Spark logical domains. We see OpenStack with its ability to, and we're getting there with that, but its ability to manage large sets and easily provision new workloads in the right kind of environment. Docker, which solves a similar problem, is part of this. And this is early enough here that I expect a lot more in this space. And hope to learn more about this in the near future. So, thank you. Thank you, Keir. Thank you, Andrew. If you have any questions, I'll be wandering around, probably having some of the snacks.
So yeah, coffee break time. There's like, so please everybody drink about a gallon. We're back here briefly for a quick intro, and then you have a tough choice between two really interesting talks for the next one. Everybody back here.
Down in Linux a long time ago, like 10 years ago. It's just that the problem was these capabilities. Yeah, there's a handful of more than 10 of those. Like root also has a capability to override all-base files. Like if the file is not edited by root, it's still can read it. So that came out as a separate capability called deck override. And there is a capability to set system time and so on and so forth. And you can actually, instead of this, it's still very chunky. I mean, it's still a big problem. This problem should be like 256 years. It's only a handful, but it's still better than root versus non-root. It's a big problem. I had a suggestion. Stuff that you might enjoy looking at. I was looking at this and thinking.
All right, can you hear me? Awesome. Great. So, yeah, big thanks to the organizing team for putting this together. Big thanks to the other sponsors. I think it's really cool to get the first Container Days here in Boston. And we at Codeship are proud to be part of it. And yeah, so I'll tell you a little bit about Codeship. Yeah, that's my tracker. Okay, yeah. So basically what we do at Codeship, we let developers focus on their code and we automate their delivery process. So basically, as you can see here, when you push code to GitHub or Bitbucket, we test it, and if everything passes, we automatically deploy it.
Hey, can I interrupt you?
Yeah.
Do you want me to videotape you?
I think it's already on the live stream.
Okay, then never
But you can, but go ahead if you want to.
All right, go ahead.
Cool. So yeah, we got a bunch of great customers like Sears Home Services or Product Hunter, WeWork. You can check it out. Go to codeship.com/customers and read case studies about how we help them solve their problems. Yeah, and of course, we love our community, and that's why we are happy to hand out swag. You can find me today and tomorrow at our little booth over there. You can see it at the Codeship sign, and grab a shirt or stickers. If we should run out of shirts, don't worry. Just head to codeship.com/swag, enter your shipping details, and we ship the swag for free to your home. All right, and of course we're always hiring, and so we're always looking for talented people. Go to codeship.com/jobs and check out. And yeah, it would be great to get some new talent and help us build a product for builders. Yeah, we do really cool team outings and team retreats. That's a picture of last summer. We went to Croatia, and of course we did a little cruise there. Basically got some boats and shipped around Croatia, so that was really nice. And in winter we headed to the Austrian Alps. And yeah, the next team retreat will happen end of September / beginning of October. So if you want to be part of something cool like this, join Codeship. Yeah, that's about it. You can approach me anytime at the booth over there. And also our engineer Nick will talk tomorrow more in depth. He's back there waving. Yeah, we'll talk tomorrow a bit more about in-depth stuff, how we do continuous delivery with Codeship. All right, thank you. So I don't know what's happening next. So.
Right now, mass migration time. Please, don't kill Anasa because he's trying to fix that door. The doors are actually the silvery things. I know. And we have to rub them all down with our lips. Later, anyway. So now we're going to have Steve Salinas talking here. I hope I got your name right, Steve. Yes, he's back there. And we have Max in the other room talking about Kubernetes. I wish I didn't have to make this kind of choice, but we are recording all the events, by the way, so if you want to watch that one later, you can do that.
Okay, well,
Just, yeah,
that guy?
Yeah.
Okay, cool.
Yeah, there's a bit of a delay, but it kicks
Yeah, it's
in
fine.
in a
I'll
second.
get there. Actual full screen.
Angled
There we go.
in a weird way.
Alright, cool.
You can use this mic, or you can use that one. With this one, you can walk
That's
around
fine,
freely.
yeah.
There's a only on-off button,
Sweet.
so you can use it as mute.
Awesome. Alright. Alright. Oh, that's really loud. Hold on a sec. Let's move that down. Alright. Okay, so I am Steven Salinas. I'm here from HubSpot to talk to you about how HubSpot does load balancing give you a talk that's partly conceptual, a little bit technical, and hopefully pretty entertaining. So I'm going to talk about first a little bit of who we are at HubSpot, who I am, what I do there, what we do as a company. I'll walk you through kind of how our infrastructure looks, mostly for some context on the real meat of the talk, how we do load balancing. And then for that, I really want to give you kind of a before and after picture of how we do load balancing and kind of how we got there and how containers actually helped us to get the infrastructure that we have today for that. So first off, as I said, I'm Steven Salinas. I'm an engineer on our PaaS team, our Platform as a Service team there at HubSpot. So what do we do? HubSpot is an all-in-one marketing and sales platform. So what does that mean? You could use WordPress to host your site and Hootsuite to manage your social media and MailChimp to do your email, or you could use HubSpot. We're kind of an all-in-one for all that. We have our own home-rolled versions of each of those different separate things. So you can imagine our infrastructure supports a lot of moving around customer data. We have Java APIs for sending email, for scheduling Twitter posts. We use things like HBase and Kafka a lot. Lots of Hadoop jobs, so there's a pretty varied amount of stuff in our infrastructure with most of the apps running in Java. So what do we do specifically on the PaaS team? So the Platform as a Service team, really we think of ourselves as managing build and deploy. But we also like to think of it that we manage developer productivity at HubSpot. So we build all the systems at HubSpot that make sure the developers don't have to worry about the infrastructure at all. They can focus on what they do best, ship their code, and have it just go and work for them. So we really try and make things as easy as possible with our systems. So a little bit of kind of stats for HubSpot. We provide this build and deploy support for over 100 developers at our company, shipping almost 1,500 separate deployable artifacts to production 150 or more times a day. And that drives traffic roughly around 9,000 requests a second across all of our load balancers that we have to maintain, routing all that traffic to over 250 web APIs and about 200 other static apps that they have to reach. So we support a lot of traffic on this. So what does this infrastructure look like that actually has to support all this? And I'll give you this for some context before we get to load balancing. So there's a couple main pieces of the HubSpot infrastructure. The first is Singularity, which is HubSpot's open source Mesos scheduler. If you haven't worked with Mesos before, Mesos basically allows us to abstract away resources like CPU and memory so that we don't have to worry about where they are in a big distributed system. It makes it very easy for us to run an elastic distributed system by just carving up the resources. So Singularity sits on that as a layer to actually schedule all the tasks that we need to run. We give Singularity information about the task, commands to run, etc. It finds the resources and goes and runs it via Mesos. The other piece that I'll talk a whole bunch more about in a minute is Baragon, another open source project from HubSpot. Baragon is our load balancer API that allows us to manipulate load balancer configuration, make sure they're valid, reload them, that kind of thing, and keep our load balancers up to date. So I'll talk a lot more about Baragon in a bit. Two more pieces. One we like to call Orion, which is kind of our UI and API that all the developers use, the nice easy deploy button basically. And it's in charge of talking to those other systems, Singularity and Baragon, to make sure that all of the data it gathers can go and deploy correctly. And then last is Deploy Service, which is basically just a big storage for all of our build and deploy data. So how does this actually look in practice? So if someone wanted to deploy. So we have our developer. Our lovely developer wants to push their changes to GitHub, and if they push their changes, it triggers a build in Jenkins. We borrow from Heroku's concept of a build pack for a lot of our builds. So a successful build results in a nice tarred up application that we can just ship off to S3 and have it in there for storage for later. Jenkins also tells our deploy service, hey, I have this successful build with this number. Its artifacts are here. Now you know about it for later. So our developer has a successful build. They want to just go hit their deploy button. It's nice and easy for them. Tells our Orion system to go ahead and gather all that information. What commit was this? Who committed it? Where's the build? Where's the artifact located? All of that information, and ship that off to Singularity. Singularity then has all the information it needs to tell Mesos to go schedule a task somewhere out in a big cluster of slave machines. So we send all that information off, it finds some resources, tells the slave to go run it, can get our tall borrow and just run our application. So that's kind of a really high-level picture of what our infrastructure looks like. So let's get more towards load balancing and how we actually are going to get our traffic to these apps. So our wonderful user obviously needs to access our application. So say they want to get to something on app.hubspot.com/hello. They'll make a request in, and it'll hit in Amazon ELB first. So each of our domains and subdomains are all fronted by an Amazon ELB. So in this case, app.hubspot.com. And backing up each of these ELBs, we have a cluster of Nginx instances that will belong to that domain and serve traffic for it. We actually chose Nginx because all of our kind of microservices are built to run on a path on some domain. So Nginx using things like location blocks is very good to route that traffic based on path. So Nginx is aware of where the app that serves -hello is and can route our traffic. So that's all good, but what's the load balancing portion of it? Obviously, if Singularity and Mesos are scheduling tasks wherever they can find a resource, we have to make sure Nginx knows that, okay, task A is now running on host A with port whatever. And we have to keep those things up to date. They can change very dynamically, very quickly. Tasks go up and down all the time. It's a click of a button to restart it and start it somewhere else, who knows where in the infrastructure. So that's why we built our load balancer API that we call Baragon. And Baragon has two main parts. The first part of it is Baragon service, which is kind of the central management piece that will take in all this information and be in charge of processing it all, making sure that path on that load balancer is actually available so we don't get conflicting things. And then you process the request, store the data, keep track of the state of the world, those kind of things. The other piece of Baragon that's really important and allows us to do a lot of this is the Baragon agent. Baragon agent sits on each of these individual Nginx instances, and it shares data with Baragon service via Zookeeper. And then it's also in charge of actually applying the configuration, writing the files, laying that down, making sure the configuration is valid, and telling Nginx, okay, reload your configuration now, and then relaying that information back to Baragon. So the way this works, each of these is also kind of grouped together. So obviously there's a couple Nginx instances behind each ELB. We don't have everything on app.hubspot.com, so they're also given a group. So say this is the app group. This will be important in a minute for how Singularity communicates with Baragon. So the app group, Baragon will know that all of the Nginx instances in this group need to have the same configuration, so that it keeps them all in sync together. They're all serving the same traffic. We have lots of resources now to serve our traffic. So Singularity has a concept of a load balance request, or so a Java API will be a load balance request. It has to be able to get traffic to it from the outside somehow. And Singularity, when a new task will come up or go down, or one will get killed, one will start up again, and it's healthy, it will need to tell Baragon, okay, I have this new healthy task. It's over on this host, running on this port. It needs to be available in this load balancer group on this path. So it'll feed that information to our Baragon service. And our Baragon service can then say, okay, I have that path open, or I know where that's supposed to be. I have that load balancer group. Baragon agents go apply this configuration. They'll check it, make sure it's valid, and make sure that everything is restarted up appropriately, and then tell Baragon service, hey, I got the configuration, we're all good to go. That feeds all the way back to Singularity, and Singularity then knows that the task is healthy, it's reachable, and we're all set to close down old tasks from an old deploy or something like that. So that's a very big kind of overall picture of how load balancing works. And it actually works pretty well for us. Singularity and Baragon keep everything in sync very nicely so that in a really kind of elastic distributed system, we're always able to reach our apps wherever they may be located. So we were thinking, how can we make this even better? How can we make it more reliable? How can we maybe save money and things like that? So we realized Mesos was great for the reliability of our applications. If one goes down, Mesos spins up a replacement right away. Why can't we also do this for load balancers? So it would give us efficient resource usage for one thing. Each of our individual Nginx instances were originally just their own Amazon AWS instance. Kind of a small instance because you don't need a ton. But each of those, even though they were pretty small, if you looked at them, they were only using maybe half or even less of the resources that they actually had. So if we can use Mesos, we can condense those down onto really big machines where we're more efficiently using the memory and CPU available to us, and we're not, paying for extra resources that we're never actually going to touch. So we can also decrease the number of servers. Before we started converting them over, we had almost 200 separate load balancer instances to maintain at HubSpot. And you can imagine there would be all sorts of headaches there. If an instance goes impaired, you have to replace it, things like that. And of course, that also saves us a lot of money if we can condense down onto 2 or 3 big instances from a couple or a couple tens of smaller instances. Another piece is that we can speed up replacement. So if an old AWS instance that serves traffic with Nginx was going to go down, we'd have to condense a new instance. We'd have to configure that instance. We have to wait for Puppet to run. If something goes wrong, we have to wait for Puppet to run again. If things don't download properly, we have to get the app running, Baragon running, and it can take a while, especially if anything goes wrong in that process. Versus if we want to run it in Mesos, we start a new Mesos task and we have a load balancer. And that was really appealing to us. We go from something that might take tens of minutes to something that probably takes tens of seconds to get a replacement up and running. And when you're serving a ton of traffic, that can be very important for the number of drop requests you have, especially if you have some catastrophic event. So we thought, how do we get there? Okay, we like this idea of running our load balancers in Mesos. And then we took a look at how we would set this up and realized that Nginx, unlike a job application, is not something you can just tar up and drop in a file system and run. You have to have all the dependent libraries installed, and we weren't about to install Nginx on every slave machine we're ever going to spin up ever, because that was just going to be a nightmare. So we decided to explore some container opportunities for this. We took around a bunch of different options, and we thought we would give Docker a try in this case. So this would allow us to not only keep some of our dependencies for this all managed together in a nice container, but also Mesos we knew had built-in Docker support, so this would be a good path for us to go down. So we started down this path trying to get a load balancer in Docker, and realized we had a couple main problems that we needed to solve. The first one was we didn't know anything about Docker. We did a bunch of experimenting with different options and realized it was going to be kind of the best for us to try first here. But we didn't have a workflow for building images, for running containers. We had to figure all that out as we went. So that was the first big piece. The second was, how are we actually going to build this image? We have a server, and we know what that server for Nginx looks like. But how are we going to actually translate that over into an image? And I'll talk about the contents of our image in a little bit. The other thing was that we needed to make sure all the restarts for this were very seamless. An instance might go up or down sometimes, but a task in Mesos, there's much more probability that it could start and stop a lot more often. And we need to make sure that in all of that, we're not dropping any requests. We're not, losing any traffic somewhere because we don't have Nginx instances behind it. So that was a pretty important piece as well. The last piece was we found kind of a conflict with how the ports were going to work. If you've worked with AWS ELBs before, they are always routing traffic to one particular port. You can't say, for this instance, route it here, for this instance, route it there, that instance there, this instance here. It's always that port. And in a very dynamic system like Mesos, where a port can be just kind of assigned from any free range, it was kind of a conflict there. So I'll talk about that in a little bit as well. So the first piece was these nice seamless restarts. And this was actually probably one of the easier pieces to solve because we already had this nice Baragon load balancer API running for us. And Baragon is pretty aware of the whole state of the world for load balancing at any given time. So by state of the world, I mean that if an Nginx instance running with Baragon comes up into a group that already exists, it can go to Zookeeper and grab all of the configuration that should be already applied for that group, apply it, and then it's good to go. So as a new instance comes up into an existing group, we can guarantee that it's going to look exactly the same as every other instance already in that group. So that was a pretty nice piece. The other things we needed to manage were agents starting up and agents shutting down. So because each of these are behind an ELB, obviously we have health checks with an ELB to see, make sure that instance is healthy, don't route traffic if it's not. But we don't want to just be building up a whole bunch of garbage things that are failing health checks in our elastic load balancers either. So Paragon Service, we also wrote a piece so that is in charge of keeping active Nginx instances in sync with what's in our ELB. So if an agent starts up, it's applied all of its configuration, it says I'm good to go, it'll notify Paragon Service, and Paragon Service will stick that in the ELB as soon as it's ready, so that a new instance can serve traffic pretty much the instant that it's ready to go. Similarly, if it's gracefully shutting down, it'll tell Paragon Service when it's shutting down, hey, you should probably take me out of the ELB. I'm not going to be here much longer. I'm about to drop all your requests. And we don't want to do that. So those two pieces were pretty easy. But we also need to manage the situation where something might just be cut out from under it. So if you've worked with Docker, restarting the Docker daemon or stopping the Docker daemon, things like that will just kind of stop your container processes sometimes. Or some catastrophic event happens, we get killed. Basically a non-graceful shutdown. We had to make sure that we could handle that. So in a non-graceful shutdown, we'd still be in our ELB. We'll probably fail health checks, but we need to make sure we get out of there as quickly as possible. So we also implemented a thing where Paragon has kind of a heartbeat for these agents running on the Nginx instances. So it knows how long since something was active and healthy. So it says, okay, I've seen this 10 seconds ago, it's probably good. 15 seconds ago, it's probably good. I haven't seen this instance in about 5 minutes. It's probably not here anymore. I'm going to get rid of that out of the ELB before it causes any problems. So we have that as kind of a backup to keep things in sync. So that was pretty good. So for seamless restarts, keep instances in that are good, put them there as soon as they're ready, take the ones out that were about to go down or about to cause us problems. So that was not too bad. So moving on to actually running and managing our containers. We had to figure out how, at HubSpot, we are now going to have a workflow for building Docker images and running Docker containers. Building Docker images was the easier part. We can use Jenkins. If it has a Docker file, build it and ship it off to our registry. That was not too bad to implement. But running containers ended up actually being quite a challenge for us to solve. So we started looking at how do we run our applications now? So how do we run them to start with? In Singularity, we've actually built our own custom Mesos executor, kind of a wrapper around the task that we're running that provides us a couple of extra benefits over the default Mesos executor. So from this, we get things like embedded artifacts that we can put in the task data, a nice S3 download service for those bigger artifacts. We get thread count monitoring to make sure something like a fork bomb doesn't take down all the rest of the apps on the server. Mesos didn't offer that at the time as one of the isolating resources. It log rotates things for us as the app is running. So if your logs are put in a certain folder, it'll log rotate, make sure you're not taking up disk space, and it'll upload those logs and index them for later so that you can actually search and grep through all of your logs for a certain service. And we really like all these features that we have, and we've used them a ton in our other applications, and we wanted to keep them if we could. So we thought, well, maybe we can figure out a way to use Mesos's Docker containerizer. So Mesos does have built-in support with their Docker containerizer for running containers. It nicely manages the lifecycle of them, create and start, map all of the ports, environment variables, all of those things very nicely. But then we realized that we needed to take a closer look at how that actually worked. So I'm going to take a minute to talk about containerizers versus executors with Mesos here. So when you're running a task on a Mesos slave, it'll start that task, whatever it may be, some shell command, within a containerizer. So the default Mesos containerizer lets you isolate that task that you're running using a number of different options. So at HubSpot, we use C groups to isolate that task in terms of memory, in terms of CPU, things like that. You can also isolate via things like disk I/O. There's a bunch of different options you can use. So that containerizer is kind of the wrapper around the actual task you're running. And if you run a custom executor, it's going to be inside that containerizer, whether it's the Docker containerizer, the Mesos containerizer, or some other one that you've written yourself. And this actually ended up being a problem for us, because while for our normal tasks, the Mesos containerizer runs right in the file system, same as everything else, it has access to the rest of, our executor has access to the rest of the slave. The Docker containerizer, that would mean basically that our executor would have to be inside our Docker container, which kind of presented a problem for us in a couple places. The first was that if it has to be inside the container, does that mean it has to be inside the image? Were we going to have to build in this custom executor into every image we built ever, along with all of its dependencies and Java and all these things that really bloat the image? And that was not going to be a good option for us. Very hard to maintain, get the right revisions out, things like that. Also, for those nice S3 upload and download services I was talking about, our custom executor needed to write to other places in the file system. And yes, Docker does things like volumes, but we don't really want to have every Docker instance ever having read-write shared volumes in the same place on the slave. That could get kind of messy. So all in all, it was kind of a sad story in the end that we really couldn't use how we were planning to go the first time through. So what we decided to do is we did decide to keep going with the Singularity executor because we wanted all those extra benefits. So we actually wrote our own Docker support for the Singularity executor. So this had to do a couple things. The first is the pretty basic manage the container lifecycle. We have to, pull the image. We have to create the container. We have to start the container, map all of the environment variables, ports, volumes, attach the container, get all of that information for logging later, and then if we're told to shut down, we need to stop the container and remove it so that we don't build up too much cruft in our on that slave machine. So that wasn't too bad. We could write that in. The executor is a Java process, so we could write calls into the Docker daemon or to the Docker engine to pull images, start and stop, whatever. The other piece of it that we really needed to manage was resource monitoring. So I talked about that we like to have the added monitoring of thread count, and that wasn't too bad for us because we could use Docker inspect, find whatever the root PID of our actual application in the container was, and use that to figure out how many threads were going. But then we ran into kind of a blocker going into CPU and memory usage. So as I mentioned before, we use C groups to isolate these tasks that are running, and actually the Mesos will use that same C group to report on how much resource usage is happening for that particular task. So when a task comes up, Mesos creates a C group somewhere in the hierarchy for it, and then all the processes for that task and all their children end up in that C group. So running something just like a straight shell command, it's not too bad because they all end up in that C group. We report on them all together. Everything is a child process of the executor, and the reporting works very nicely. But with Docker, when we're running a Docker image, or running a Docker container, the container process is no longer a child of our executor. It's actually a child of the Docker daemon, which makes the reporting on that quite different. So we were looking at this, and we were realizing that the CPU and memory for every Docker container process we were looking at was the same, because it was just the CPU and memory for the executor and maybe Docker attach. So it really wasn't giving us any accurate, usable data that we were going to need to be able to run these containers reliably and monitor them reliably in a more production kind of setting. So we were doing all sorts of things, manually moving processes around, echoing things between C groups, and it was a big old mess. I would not suggest trying to do that. We tried to do this in a bunch of different ways. I mangled many VMs and C groups trying to get it to work, and it really just wasn't a great option. Then, as we were developing this, out came Docker 1.6. If there's someone from Docker in the audience here, we love you for this option. Docker 1.6 has a new option called cgroup parent. And cgroup parent means that your container can run underneath the hierarchy of any C group that you tell it to. So in this case, when we're starting up our container, we tell it to run as a child C group of whatever that Mesos executor C group is for the task that we're running. So because we're running as a child C group, then we can use C group's hierarchy in order to actually report all of the memory usage correctly. So if we enable hierarchy for that Mesos executor C group, then it not only reports the memory of what's in that group, but what's in all the child groups. So then we're getting memory reporting for our executor for any monitoring processes and the log rotate and all of that stuff, but also for the entire app in the container. So now we have an actual realistic view of the resources being used for our containers, and we can run them, monitor them appropriately. And as an added bonus, our at the upgrade registry, we made our pulls faster, so we weren't timing out waiting for images to download, which was a good thing too. So now we can run containers. We can build our images. What are we actually going to put in this image that's going to be our load balancer? So there were three main pieces that we wanted to put in it. And the first is Nginx. Of course, we need our functionality. We talked about the Baragon agent, which manages all the configuration. And then we also, on our server, we had a bunch of monitoring. We were fond of our Kaiju at the past team there, and it's called Rodan. If you look in our GitHub, things like Kumanga make an appearance too. So we wanted to put all of this in there, and yes, we realized that this kind of goes against a bunch of the single process per container thing. But we had some reasoning behind that. The first was that Nginx and Baragon are very, very tightly linked. They had to be able, Nginx had to be able to run right next to it so Baragon could call Nginx executables and things like that. But also, there was not an easy way to run linked containers in Mesos. So if we spun them up as separate tasks, there's no real way we can guarantee that they're going to be on the same slave machine when they come up. So even if we could link them together in a really nice way, if they're running on two separate slave machines, that doesn't do us any good anyways. We can't access the file system nicely, and there wasn't really a way to accomplish that easily without rolling something ourselves. That was going to be pretty complicated. So we decided to go down the multiple processes in a container path for this particular application. So our first attempt at this, which didn't work, is we thought, okay, well, we're new to Docker. Let's mimic what the server looks like, and we'll see where it goes from there. So we installed Nginx. We installed Java for our Baragon agent. We installed Python for some monitoring things. We yum install, all sorts of things. We put our app in there, our monitoring app in there, all the configuration in there, and before you know it, we have this big bloated image that's 2.5 gigs. Mesos is trying to download it, and it's timing out, trying to even start our process because it's only halfway through downloading the image by the time we're, saying, okay, you should have really been running by now. So that was kind of, a failure of an attempt there. But so we said, okay, let's put this image on a diet. Let's really slim it down a lot so that we have a, a nice, fast, lean image that we can run for all these containers. So we started with the CentOS-based image. The rest of our infrastructure was already running in CentOS, so it just seemed like a logical choice for us. And then we did very minimal library installs. So obviously we need, Nginx installed. We need Java to run, but we went as far as even removing pieces of the JDK that we weren't going to use, so that we really save as much space as possible in this image, and we're not downloading any extras or files that we're never going to touch, basically. So we also decided to kind of change how things were going to run within the container. So I talked about that each of those Nginx clusters belongs to a group kind of behind one domain. You can imagine that not every single domain is going to have the same exact configuration. So our nginx.conf kind of file, we need to put the domain in there. We need to put all sorts of different things in there that might change per domain. So we actually had a kind of a start script that would template out all these things based on environment variables we passed into the container, so that whatever group we were running, the same image could run, app.hubspot or something else.hubspot. It didn't really matter. As long as we just told it what group it was, it could template out all the configuration and just run it. So that then ran Supervisor. Supervisor, pretty popular for running multiple apps within a container. And Supervisor obviously needs to start Nginx. And it also starts what we call Distributed Deploy Updater, which is kind of a unique piece to our infrastructure that I'll talk about in just a second. But overall, this was a very good thing for us. The image came down to about 450 megabytes from there, which is very manageable, pretty quick to download based on CentOS. So if we pre-download CentOS on all of them, it's very, very fast, pretty snappy. In terms of how it ran, so he's asking if we noticed a difference in CPU memory, obviously space utilization, when we switched over to this more lean image. So the first, I guess they were hard to compare, I guess is what I want to say, because the first one really was almost like a full server VM. We never really got it running in the Mesos type environment. We were able to get it running locally, but because of the constraints for downloading it so long and things like that, and we were also still in the process of getting the memory and CPU reporting appropriately while we were doing that. It was slower, to be sure. Maybe even if it was pre-downloaded, it would take about a minute or so to get everything up and running. So there was that. This is definitely a lot faster. In the end, we're kind of getting in the tens of seconds range for things to start up. Yeah. Can we get through one more thing and then I'll do questions, or is it on this part? Yeah, sure. So we thought of that. The first thing was that we have our own custom build of Nginx that we use, and for the rest of our infrastructure is all CentOS already. So rather than rebuilding another custom build of Nginx that can install on BusyBox or install on the slightly smaller Ubuntu image, we thought, just go with CentOS, especially because at the time this was a very proof of concept kind of idea. How can we get it running is, yeah. So we went with the kind of short path to getting it running well. Yeah. So I guess the thing I want to point out is, you notice I didn't actually talk about putting the applications like Baragon and Rodan for monitoring in this at all. And that's where that distributed deploy updater comes in, which actually allows us to do some pretty cool things. So we have this concept at HubSpot of distributed or kind of inverse deploys. So what this is, it's a small Python package that we use in a bunch of other places in our infrastructure. And it watches that deploy service where all the build and deploy data is stored to see if a new version of that application has been deployed. So in this way, we just have this small Python package watching out there to see what's happening, and it will download the app. If it sees that, oh, there's a new deploy, and that's not the version I have in my file system, I should download it, stop the old one, start the new one. So that actually allowed us to do a couple really cool things for the image. The first is that obviously we don't need to store these app artifacts in our image anymore, which saves us a lot of space in the image. It's a little bit faster still to download something straight from S3 versus downloading it from a Docker registry. So it saved us a little time there. But we also then could update and kind of redeploy the managing and monitoring apps without ever having to interrupt Nginx. So when we're serving a bunch of traffic, yes, we did a lot of work to make sure that these stops and starts are going to work appropriately, but why interrupt Nginx serving traffic when we don't have to? So in this way, we can do deploys of Baragon, Rodan, without having to rebuild the entire container, go and restart all the containers and restart all the load balancers, take a whole cluster of them, add the ELB, put a whole new cluster in. So it actually saves us kind of a lot of maintenance headache there and works a lot more similar to how our servers work now. So that's distributed deploys. So the last problem that I talked about is managing ports. So the AWS ELBs expect Nginx to always be listening on the exact same port. You tell it, traffic coming in on port 80 to the ELB goes to traffic port 8080 on Nginx. For any instance you ever add, it's going to want to put it on 8080. So Mesos is a lot more dynamic. You could get any port that happens to be free within a certain range. And obviously that wouldn't work very well. We don't know what port we're going to get. We can't always guarantee that it's going to be the same. So having instances popping up here and there on different ports wasn't going to work very well. And we thought, Docker port mapping might be nice. But while we could make that consistent within the container, so Nginx always thinks in the container it's running on port 80. When it's exposed to the outside, that could be still any number of ports that happen to be open at the time. So neither of those were going to really work for us in this particular instance. So we had to come up with a strategy for this. The first piece of this was that we were going to terminate SSL at our ELBs. So now instead of needing a port for regular traffic and a port for SSL traffic, we only needed one static port. So sort of cut our problem in half without really solving it yet. But the thing that we actually did to solve this is each of those groups, so app or whatever it may be, was assigned one static port outside of the range that Mesos was going to assign things to. So if you're an app load balancer, you're always going to run on port, 41 something, something, something. In this way, that we could make sure that that same static port is always available for the ELB. We also, in Singularity, have a concept of separate placement for tasks, meaning that all the tasks within a certain group or for a certain service no two of those tasks will ever run on the same slave machine. And Singularity can guarantee that for us. So in that way, we won't actually get any port conflicts because two of these containers came up on the same machine. So every group will be different, and no two of the same group will run the same machine. No port conflicts there, which was nice. We also want to do one more thing that gets a little tricky with the ports. And so Singularity, when it does its health checks, actually just whatever that first port is that it assigns you from that random range, it does its health check on that port. And that's how it works right now. So we want Nginx to also listen on that dynamic port to make sure that we can tell Nginx is up and Baragon is up so that we really know the container is healthy and running correctly before Singularity says, okay, it's good to go, let's shut down the old ones. We don't want to shut them all down when Nginx isn't actually running. So each Nginx instance also has some configuration kind of pre-stamped into it that will route traffic to where it expects Baragon agent to eventually be. So in this way, we're making sure that traffic can go through Nginx, Baragon can serve a request and is up and running, meaning that all the pieces, all the essential necessary pieces of our container are actually running, and we know it's healthy before we shut things down. All right, so we did all of this. What did we actually see out of it here? The big thing and the big goal for us was reliability. So first of all, no more getting paged for instances that go impaired. You don't have to, get up at 3 a.m. to replace a load balancer because it happened to, just stop accepting connections for some reason. It also removed most of the human intervention from management of load balancers for us, which was really nice. It's now more of a, click a button to deploy, or click a button to spin up a new one, click a button to scale, things like that. And all the configuration is managed automatically for us by the API. It's also very fast replacement. I talked of that tens of seconds versus tens of minutes. Last I checked, the fastest one, if the image is already downloaded, spun up in about 10 seconds. And some of the slower ones were in the 15 to 20 second range. So it's really, really fast to get it going. Nginx starts right away, and then as soon as the Baragon agent application gets downloaded and started up by our distributed deploy, we're all set to go. And that was very quick, which was very nice. We also have a little bit of extra resources available to us on those nice big Meso slave machines. So instead of running on a machine that might have one CPU and 4 gigs of memory in a burst kind of situation where we all of a sudden get a bunch of traffic at once, we're now on a machine that has some hundreds of gigs of memory and 64 CPUs. So we have those extra resources available to us to kind of give us a boost in the case where we need it, which is very nice too. Scalability, I mentioned too, is now just one click. If we need more load balancers for a certain group because we're getting a lot of traffic, we click the scale button in Singularity and we have more load balancers. It's very, very simple, very, very quick. No more spinning up new instances. Last piece, obviously, is cost. We're still in the process of converting a lot of these load balancers over, but every time we throw one in Mesos, we can shut a server down. We can run it mixed in with all the existing infrastructure we have, maybe add 2 or 3, big, huge Meso slave machines to replace 20 or 30 of these small load balancer machines. Gives us better utilization of the resources that we're actually paying for. Obviously, it saves us a bunch of money overall, which is really nice. So coming down to the end here, if you want to check out Baragon or Singularity, you can check them out on our HubSpot GitHub. Both are completely open source. There's also images published on the public Docker Hub for Baragon Service, Baragon Agent, and Singularity. And in both of those, there's also working Docker Compose examples. So if you want to try out Singularity with Baragon as a load balancer paired together, you can actually go to the repository, pull the images, and just run Docker Compose up to get a full Mesos cluster with Singularity and Baragon running in it as well. So hope you enjoyed. Again, I'm Steven Salinas. Tom's here from HubSpot 2. We'll be here all day. We'll be at drinks tonight. So come talk to us if you have anything you want to say. Any questions? Yeah. So the way a request out to it works, when we make a request to run a task, we say this task needs at most this much memory, at most this many CPUs, and it's allowed to use up to that much. So it'll commit that much, and it'll reserve that much. So if we go, if we go over that memory, it'll kill the task. There, it's still reserved for that task. No one else can come steal that. Yeah, yeah.
Thanks. So you said that one of the problems that you were trying to solve was every time you needed to bring up a new web server, it could take many minutes to do that because it was a machine. So it seems that when you adopt Docker, what's happening is you're sort of shifting that because it just changes the capacity planning. You don't have the extra capacity in those machines to sort of help you with the spike. And eventually you're going to run out of machines to put containers on and need to provision a machine anyway.
Right.
So have you guys run into that? And if so, how are you dealing with it?
So we haven't run into that just yet. We don't do a lot of like auto scaling at HubSpot right now. Our traffic is actually pretty static during the day compared to some other places that might get a whole ton of traffic around dinner time, that kind of thing. Our traffic is actually pretty static, so we don't do a lot of auto scaling. We try and keep a good buffer of extra resources on the machines at any given time. We haven't really run into the problem just yet of seeing we need more, but there's not enough space. We try and make sure, especially with how many apps and things we have to run that can be pretty big sometimes, there's always kind of a buffer of extra CPU and memory available. Exactly, yeah. Making sure the overall has enough, keep a buffer in there for something of an emergency that might come up or a large job that'll come through. Yeah.
Next to hook up to the ALB, could you have used, or did you look into using like a host mode instead of a bridge mode for the Docker container, so you can use a static port basically?
We did look at that. So like I said, Nginx could be on I guess the problem we had with ports was more that Mesos assigns us a dynamic port, and that if we are using bridge mode, yes, Nginx sees it as always port 80 from inside the instance, but we needed that static port outside too. We mostly needed a way to guarantee that the outside accessible way to Nginx was always on the same port, which within the Mesos range was not going to be possible. The way Mesos considers the available ports also kind of a resource that it's scheduling. So does that sort of answer your question? Sorry, maybe I heard it wrong.
Host mode would have basically not having this bridge and this dual port. You would basically, the port that you expose would be the port that you see outside.
Yeah, so we are running in host mode. Sorry, I misheard your question. We are running the containers in host mode right now. We started off trying bridge mode, but we realized we were just doing bridge mode, mapping the same port to the same port, and it didn't really make sense to be running a bridge that way, especially when host mode. It's a little more direct and might give us some performance benefit out of that for Nginx too. Yeah, no problem.
Dynamic resource. Thank you. You described your daemon that you run. It's made of Python, and it runs inside your container, and it looks for updates from your updater thing. That reminds me so strongly of Chef. Like, that's more or less what you're doing. You're updating, like you're pulling dynamic updates because you're running multiple apps inside your container, and some of them you want to update on a different schedule than the others.
Right.
Do you install Linux packages for these things? What sort of resources are you pulling down from S3 and updating?
Like I said, when we build in Jenkins, we do the Heroku build pack kind of thing. So it's just a nice tarred up application. The only thing we really needed to install in the image itself was just kind of the base dependencies. Like we needed Java to run this one app, and actually our monitoring app runs in Java as well. So we just needed the very base dependencies that we would have, on a normal Mesos slave somewhere. So we're not actually doing, any more like yum install when we download a new app. The app, if it has dependencies in it, like for a Python app, for example, we actually bundle all the dependencies, all the dependency libraries in with that tar file, so that when we download it, we have it all available to us right from the get-go, no installs to do. The goal of how we package our apps is just that download, run. Does that answer your question? Okay. Yeah. So Singularity was actually built before I came to HubSpot. I know I don't know, maybe Tom can talk better to that one, maybe after the talk or something like that. But it's, if do you want Mike for a second? Tom here was one of the ones that helped actually build Singularity.
Yeah, so we actually looked at using Marathon and Kronos in the beginning when we first started looking at Mesos, and I think they're great pieces of software, but they kind of follow that Unix metaphor that Mesosphere is really into about how Mesos is your data center's kernel, and Marathon is Upstart and Kronos is cron. We didn't want to have to deal with all the plumbing there. So the idea of Singularity is it's pass in a box. You can deploy to Singularity and it'll run your stuff. There's no extra plumbing that you need to do. So that's basically why.
Any other questions for Stephen?
Say it one more. Sorry, say it one more time.
I ask, hello. Yeah. I ask, why did you choose Mesos? Why that's over other paths like Cloud Foundry or Heroku, some other options?
So for one thing, with things like Heroku, we manage all our infrastructure in-house. So we were looking for kind of a open source, something we could use ourselves versus shipping our applications off somewhere else to have someone else run them and manage them for us. We wanted to do all that inside. Mesos also just offered the great reliability benefits. Abstracting away things like CPU and memory from machines so that we just have a big cluster of everything rather than saying this app runs on this machine, this app runs on that machine. It gave us a lot of flexibility in being able to. I believe Cloud Foundry is doing similar, yeah.
Thank you very much to Stephen and Coach, and HubSpot for an amazing presentation.
Oops, I should turn this off.
That's exactly what all the people at Docker Austin are asking for is how do I get started? So like you started with I attempted, this is how it failed, this is what we then thought. That's fantastic. Thanks. Oh, thanks for having me. It was a lot of fun. Yeah, so thanks so much. To this question, we have a Golang binary. I took a 700. BusyBox and just the Go binary. About 50%. Oh, really? Yeah, just on nothing else was different. The same binary was running. Yeah. So we don't, and I could never get anybody to answer me about what's going on internally.
Probably has to do a lot with actually the storage backend. So if you have a lot more layers to your image that you're going through every time you're doing, even just rewrites from a file system, depending on what storage driver you're using, you're spending a lot of extra time moving through all those images, making sure that the copy on write style.
Yeah, the copy on write. I never thought about that.
Yeah. Our images do run faster,
So
especially
if I
on
had to
things like.
squash the bigger image, it would have.
No, it'd be worth a try, especially if you're running like on Ops or something like that instead of device mapper. It's probably worth a try.
I wanted to look at that. That's great. Thanks.
How you doing?
Tom. JJ. Pretty good.
Just a quick question. If you just have usually infrastructure, you have to do
So we had to be really careful about moving containers when we're doing them and things like that. We actually did hit a point where we had
Here's the, yeah, exactly, do that. Here's,
I'll propose that one tomorrow, is what I was going to say.
oh, okay, we can do that as well. Put it on the board.
so you're like running
go watch it to make sure that
All right, everyone.
Right, that, okay, we're almost good for time, not too far behind. So, the start of the open spaces concept for today. Hopefully you've got some food for thought out of what you've heard so far, or you've come prepared with some questions, but yeah, who does homework? I never do homework, so I don't expect anybody else to. We're only going to do this Ignite off, short presentation of these topics for this first one.
The way, and then for the second one, we'll just assume that it'll happen organically as people have coffee, as they sit in a session. So the way it's going to work for this first one, Boyd will demonstrate in a second how a presentation of a topic works. You get about 10 or 20 or 30 seconds to introduce your topic. You write the topic, a short summary, on one of the post-it notes that's behind the desk there. And then when you've done, you go outside to where the lounge area is. There's that piece of paper on the wall, and you pin your post-it note on the wall. Everybody else stays in. We'll vote on them when we're done. And if you, as you're thinking and listening about this, if you have a topic that you want to propose, you go and stand in a line behind Boyd over there. That's how we're going to do this first one. So everybody's going to propose a topic for 10 or 20 seconds. Go outside, put it on the sticky board. We'll vote on it after that. Then we'll go actually into the various locations and talk about this stuff. There are 4 locations again. There's this one, the room where you've been. There's just by the patio over there is the VM turbo space. And right at the end of the corridor, past the restrooms on the left, is the 4th room. That's the SysDig room. There's another open spaces session later on today. What we're going to do for that, once you've got a bit of a hang of the concept, there are going to be 2 tables with post-it notes next to the wall, that wall chart. If you think of an interesting topic in the course of the day by speaking to vendors or whatever, just write the topic down on a post-it note, put it up on the chart. Have a look at what is posted on there. If you want to vote on one of those instead, do that. Then just before the second open spaces session, which is the last session of the day at about 4:20 or so, we will pick the 4 most voted sessions, and we'll have another open spaces until we all go and have a beer or a glass of wine or whatever. Does that make sense? Cool. All right, so now Boyd will demonstrate how the first one works.
One thing I'd ask that you all do, it'll be very much easier if you'll write your topics towards the top of your post-it note so that the people voting, you're going to make a dot. They're all at the bottom. It'll just make that a lot easier to count, and it'll make it a lot easier for us to get through as the organizers. Thank you. Okay, so my first proposal. There's a lot of information out there about Docker. What I'd like to do is I'd like to show you how to start a Docker development environment. I'm going to spin up a Python app, and I'm going to show you how to put this on your Mac, on your Windows machine, with something called boot to Docker. So if you would actually like to go through this with me, I'll ask right now that you start downloading boot to Docker because it brings down Oracle's, help me, VBox, VirtualBox, all right, which is a rather large download. We don't all want to hit that button at the same time and screw everybody out of the internet. So if you are interested in learning how to bring up a Docker development environment, if you're new to Docker, if you want to see how disposable development environments work, you've heard about Vagrant, you've heard about Docker, those sorts of things, come check it out. Thanks. Thanks.
So if you want to propose a topic, please come and line up behind me, because that's where, don't be shy. This is not a sit-down session. This is meant to be an interactive session. So I'll do the next one, because I was in line behind myself. That's a kind of slightly problem there. So my suggestion is how to run a secure image hub. And what prompted this question is a recent blog post that some of you may have read, that roughly 70% of the images that are currently on the public Docker hub contain serious security vulnerabilities. They're vulnerable to Heartbleed, or they're vulnerable to whatever. That's obviously a bit of a challenge if you want to run this kind of stuff in production. So, I would like to discuss. I don't have the answer. Anybody whether they're keeping it internal, so I'm not going to go and do the whole talk now, but I would like to know what kind of approaches people have, what other things from other technologies people can throw in. That's really what I'd like to talk about.
Sound check. Okay. I can talk about LXC or LXD as one of the main LXC contributors. I can also try to help answer your questions. We can go through about the differences between application containers and system containers and such stuff like that. Else?
Okay, well, my name's Dave, and if nobody's going to propose it, then I will. How about a session on how does containers change the developer workflow? How do I get started with that? I'm going to make sure I don't conflict with Boyd's session, so hopefully we can do it after that or something like that. Do we have more than one round? Do we have more than one round of unconference for this part?
Yes, there's 2 open spaces sessions today, and then there's one more tomorrow.
Okay, so I'll make sure not to conflict with that. And if yeah,
exactly.
yeah. So if you're interested in that, I'll just put like developer workflow with containers, something like that.
And then we should have a ban on organizers suggesting sessions. That's not the point, guys. You can talk about anything you want to talk about. So whether it's security, versions, plugins, storage, networking, why am I even here? You know, anything, right? So don't be shy.
Oh, sorry. Okay, my name is Issa with BitSite. I wanted to talk about networking and how if you have a current network setup and you're trying to integrate Docker both locally and in your cloud, you know, what are you doing network-wise? I don't really have answers, so if someone's a little bit more familiar with that Docker networking, I'd love to talk to you.
My name is Matt, and I'd like to propose a topic on logging from containers. I work for a company that has a solution. I'm interested in learning how people are currently doing it. I'm interested in learning about other solutions.
Matt, make sure you write it down and post it out there so people can vote on it.
I will.
How's it going? My name is Ryan Wallner. I work for EMC and would love to talk about data persistence if you're working on running databases and containers or worried about kind of the security aspects of putting volumes or working with volumes. Love to talk about it.
Hey everyone, my name is Dustin, Boston DevOps. If you've not been to it, go to it. I want to talk about configuration management and containers because from what I've seen, unless you have a very simple application, a Docker file is probably not going to cut it. So how are people pre-baking images using things like Chef and Puppet and then layering things on top of them?
So I'm fairly new to containers, and I see there's like a bunch of topics about different ways to do like container management. I'd be interested in just seeing kind of like a high level, maybe architecture of people's interpretations of what container management means. We talk about scheduling and logging and the different product sets that kind of fit in. So just kind of a high level view of, you know, this is what's used for scheduling, this is what's used for clustering, logging, and maybe the different approaches that different people take.
Hi, my name is Ravi. I'm from EMC. I'd like to propose that we talk about or discuss scaling containers to web scale. So there's this new buzzword going on, web scale technologies, web scale everything. And so we want to understand what some of the approaches are, but scaling containers to make it web scale, truly web scale, make it more dynamic, elastic, resilient, and things like that. So that's my topic.
Outside, or there's a big white piece of paper. Does anybody else have a proposal they'd like to make?
Hello, I'd like to demonstrate the brand new Curses UI for the open source Sysdig tool. It's by far the best, easiest way to explore and gain visibility into all your containers right from the command line. Super fun.
Write it down so yeah, can get voted. Okay, while Kira's getting his together, does anybody else have a proposal they'd like to make? Yeah, you're Kira, right?
Hi, my name's Kier, and I would like to propose a topic of containers live migration, how it's done, what you can do with it, how it changes your workflow, and so on and so forth. So this is it. Live migration.
Other topics? I'm really upset that I proposed the topic, because now I don't get to go to those.
You can take it back.
Anybody else? Going once?
Going twice.
Sold!
All right. So, and now we'll go and vote. So there's stickies out on the board. I'll bring more pens so we can parallelize the process. And then you can find, just put dots on the stickies that you're interested in, the post-it notes, and then we'll figure out what actually gets talked about. These are containers of ink. You need to put your ink.
That might be day 2 schedule.
Yep. Yeah, I just want to take a look at it.
Does this work? Oh, it does work now. Right. We have some stragglers, but we will not wait for the stragglers because we want to get going a little bit. So 2 quick housekeeping things. First of all, that kind of turned into a bit of a working lunch, which was great. But what it did do is it deprived Andrew from Localytics, our lunch sponsor, from saying something and saying why they sponsored lunch. So I'll let him do that very briefly.
First time I got an ovation for lunch. Hi everyone, my name's Andrew. I'm one of the co-founders of a company here in Boston called Localytics. We do mobile app marketing, automation, and analytics. We're about 250 people located downtown Crossing. We develop a lot on Amazon Web Services, do a ton of stuff with the containers, write a lot of code in Scala, Ruby, JavaScript, all that kind of stuff. Definitely hiring for anyone at any part of the stack, whether you're front end, back end, anything like that. If you can come find me if you were curious, or there's a couple other people walking around with Localytics shirts on. There's Sean Edwards in the back. Chris Jelly's walking around too. He's got a shirt on, a Localytics shirt on. But yeah, also later tonight, we're doing this thing that we call Free Beer Friday. It's once a month. If you go and get drinks as part of this event, come join us maybe afterwards at the Localytics office, 101 Arch Street downtown. Just ask me where that is. We'll be there about probably until 9 o'clock at least. But yeah, thank you.
Thank you, Andrew. I like that name. It's a really good name. So yeah, and the good thing is that clearly the free beer tab from us will run out before 9 o'clock. So if you feel you want some more, then Localytics is the place to go. One of the things, if you arrived later today, you might not have heard at the beginning. We are here tomorrow on this floor again because of some construction, which means that the ceiling will cave in or something if we make too much noise. I don't know. In any case, we are here tomorrow, not on the 11th floor, so that should be easy, especially if you wake up with a hangover. Just come back to the same place. We are moving the program forward. Well, we're trying to. I probably won't, by about 10 minutes, because that allows us to have a 45-minute open spaces session at the end of the day, and not 35 minutes. And at the end of the day, don't run away, because you will be getting, if you want to come to the Friday, the drinks event that's actually part of Container Days, you will get your drinks tickets from the people who are sponsoring the drinks. That's, I guess, the classic. So without further ado, let me hand over. We have 2 more sponsor shout-outs before we get into our next session. And the first one is Sysdig.
Hi, everyone. I hope everyone's having a good event here at Containers Day Boston. I'm Mike Fox. I'm here with Sysdig. We have a table out front. Feel free to stop by. Essentially, I'll keep this real short. Just wanted to make an introduction. Essentially, Sysdig is started off as an open source project. It is think of it as a Linux utility tool for troubleshooting system events. We also just recently announced a new Curses UI, which is pretty sweet and has been picking up some interesting comments on Twitter. So feel free to check that out. We also took the core technology behind this open source project and built a distributed SaaS version, which essentially gives you full visibility into your applications network and down to your infrastructure, including Docker containers. Some of the really cool things about it is you don't have to install an agent inside each individual container. It's either in its own privileged container or on the host node itself. So feel free to check that out if it's of interest, and stop by the booth. We'd love to hear from you and learn how you're using containers today. Last thing I'll leave you with here is just to show you a quick image of the app itself to get a sense of what we're doing around containers. As I switch over to the UI here, we're able to automatically build topology views of your application. This is a small demo stack running in AWS. It's a WordPress app, and essentially we're able to break out your cluster views, drill into each tier to see each individual node that is making up of that front end, and then from there we're able to drill down, automatically detect all of the process level information as well as the containers themselves with those processes running inside. So if you're looking for visibility like this out of the box, please do feel free to stop by. We'd love to chat. Thanks, and enjoy the rest of the conference.
Woo! Woo! Hi, my name is Boyd Hemphill. So the camera stops kind of here, by the way, for anybody else. So if you go beyond this, then you disappear off image.
Okay, thank you. Gotta have that on camera. All right. Hi, my name is Boyd Hemphill. I'm several people. First of all, I am the guy who is behind Container Days Austin, the first one of these ever. Because back in October, I went looking for containerdays.org as a domain, and I found this guy, Andrew Phillips. And I said, hey, what are you going to do with that? And he said, well, I'm going to have a conference. And I'm like, cool, me too. So we got to working together. We found Dave Nielsen, who is of CloudCamp fame. And we did the first one in Austin at the end of March. It was really cool. And this is even cooler. And it is. And we're already talking about the next one. So thank you guys for your support. Thanks for coming out. I mean, we know that your time is valuable. And you coming here was a choice about how you wish to spend that time. Thank you.
Well, all right. They kidnapped some of their children, so.
Oh, I got to use that strategy next time. All right. So with that said, all right. Now I'm Boyd Hemphill, the sponsor. All right. So I work for a company called Stack Engine. We're located in Austin, Texas. We do container management, orchestration, and scheduling. So if you're interested in these sorts of things, if you're working on getting your first topology in Docker out, we can give you a lot of information about that. We intend to make a very big splash at DockerCon here at the end of the month. So keep your eyes peeled. And in the meantime, please come and check us out, stackengine.com. To that end, I have bribery. Now I'm Boyd Hemphill, the marketing guy. I want your contact information, people. I want to bug you.
How you throw the eggs?
For that, you will have a chance to win your very own container ship because it is Container Days after all, right? So please come by the Stack Engine table, drop your card, or just write on one of those Post-it notes there your name, your company, and your email address, and we'll find you. And at the end of the day tomorrow, we'll do a raffle with any of the other sponsors who are going to do such. Thank you very much for your time, and again, thank you for supporting Container Days.
Thank you, boy.
And now for the next presentation, we are first going to have another AV moment and see whether this system holds up. And when that is all done, we have a Docker Tinkerer Extraordinaire, Mr. Jerome Pettazzoni. I don't know whether I got that one right.
That's okay.
It's good enough.
So yeah, and then, you know,
The end of the, stuff is not happening. Stuff is not happening. Oh, well, we're a little early, so that's all good. Let me go grab let me go grab, there he comes. Yeah. Anastas, do you know what's going on here? Blanks. Oh, that was so tempting. So tempting. It was there a second ago, and then it sort of disappeared. It was up, and then it was down. Ah! Uh-oh. Now it's on the left one.
It's still on the next.
Okay. Now it's on the left one.
It takes a moment. Okay, good.
Ta-da!
all right. So let's see. Mode, clicker, laser, check. Timing, check. And let's do this. All right, so we want to talk about separation of concerns with Docker and containers, and I will explain what this means. And if I move over here, I think you won't hear me anymore, so I should remain around here. So short intro, I'm Jerome Pettazzoni. I work for Docker. I work for Docker even when it was not Docker yet, so I'm a kind of hipster of containers because I was doing that even when it wasn't cool yet. So back in the days when I started with containers, I was working on .cloud. That was platform as a service. We started that almost 5 years ago, and we're using containers in production at scale. So I picked up a few tips and tricks about running containers. So the intro for today is that the outline for today is that I want to do an extremely short intro about Docker because I guess you already know a lot about it. So I don't want to get it to be too boring to like explain what is Docker since most of you already know. But I will try to drop some bits of useful knowledge during this intro to make that interesting nonetheless. Then I will talk about some of the differences between VMs and containers. And the goal is not to make like, containers are better or worse because this and this. The goal is to see from those differences what kind of things we can extract to build something that I will call lean containers, so that are containers that have just what we need, and then we can add other containers next to them to implement extra features like logging and backups and monitoring, all the things that you don't typically need in development, but that you need in production. So let's do this. First, quick recap about Docker and containers. As you probably know, the Docker motto is like build, ship, and run any app anywhere. And I decided to break this down to see exactly what it means. So first, build means take any Linux program and put it in a container. Can you raise your hand if you already know that you can take like web apps and other services and put them in containers? So virtually everybody, of course. You probably maybe also know that you can put data stores in containers. Less people, so either people are tired or raising their hands or something. But yeah, you can put data stores in containers as well. Other stuff like console, etcd, RabbitMQ, Zookeeper. Anybody doing that? Not a few. Yeah, okay. Command line tools, for instance, the Amazon command line. Each time I need to do something with that, I end up having to install what used to be Java. Now it's some Python stuff, and it's kind of boring. Now I can run that in a container. So when I need to install something on the command line, I can install a container instead. Does anybody here does that already? A few people. And now something that you probably don't know unless you happen to see Jessica Frazel's talk at Container Camp in San Francisco or other stuff like that. You can put desktop applications in containers. Anybody doing that? A few persons, great. Yeah, you can actually put like Chrome, OpenOffice, Skype, Steam, all that stuff can run in containers. So down the road, I think we will end up having pretty much everything in containers. What about non-Linux programs? So you can also put Windows applications using Wine in containers, and that's actually a pretty good way to deploy them because Wine is a kind of tricky thing to set up, but if you put that in a container, then you do the hard work once and put that in a container, and that container can work everywhere. I'm pretty sure that nobody really saw that coming. One thing that I absolutely did not see coming is Docker on Windows. And a couple of years ago, when I was doing the first talks about Docker, I was joking about the fact that there would never ever be Docker on Windows. Turns out I was wrong, jokes on me, because Microsoft is working on that. They made some pretty cool demos at Build, I think, last month. And so Docker on Windows is coming. There are people working on a Docker for FreeBSD port as well, and there is maybe someday Docker for OS X, because at that point, when you have Docker almost everywhere, why not get it on some of the most popular developer environment today? So then the second part of build, ship, and run is ship. So with Docker, we can ship those containers easily by breaking them down in small layers and shipping only the layers that changed. So that makes it easier to ship containers compared to VMs, because instead of shipping a 10 gigs VM image, we can ship smaller layers, and that's much faster, especially when you don't have a super fast fiber coming straight to your development machine. And the last step in build, ship, and run is run. So containers give us a way to run both on physical and virtual machines, so that's great, hybrid cloud and things like that. Docker is available on all modern Linux kernels. That changed quite a bit since like 2 years ago, when Docker only ran if you had Debian or Ubuntu kernels with AUFS. Most cloud providers today have several images to run Docker. There are distros that have been made like from the ground up just for the sole purpose of running containers, like Atomic, CoreOS, SnappyCore. RencherOS is also pretty cool. Almost 2 years ago, I remember talking with some Rackspace folks about, hey, it could be nice if we could use like Docker as PID1, Pipedream and everything. Turns out that Rancher Labs did that, and RencherOS is actually a Linux distro where Docker runs as PID1, among other nice things. There are other Docker implementations available. There is Joyent, the people that are kind of still maintaining Solaris and all that amazing stack, have something called Triton, which is part of their smart data center thing, and that lets you run Docker containers as Solaris zones. So the code base has almost nothing in common with the Docker code base, but the API is the same, so you can point your Docker client to that and run containers inside Solaris. And there are many Docker as a service things that are appearing every day. I think yesterday or 2 days ago, there was ProfitBricks, I think, who announced that they were launching something to host Docker containers as well. Anyway, so let's talk a little bit about the differences between VMs and container. And I want to stress out that the goal is not to make like a kind of scoring card, but rather to see what kind of different beasts VMs and containers are, to see how we can leverage on those differences to make something really cool. From a portability point of view, containers can run pretty much anywhere. So if I have a container, I can deploy that on EC2. Contrast to when I have a VM, if I want to deploy that VM on EC2, that's kind of complicated, because even if technically today we can run VMs within VMs, like nested hypervisors, and those things exist, but it's not really easy to do that on EC2. I'm not going to say impossible, because then someone will tell me, no, we did it. But it's hard enough so that if you look for it, the answer is not obvious. So containers give us at least something that we can move around really easily. From the format point of view, I wanted to make a kind of, not really a comparison, but more like let's try to map concepts between VMs, as in like PC virtual machines, the JVM, the Java Virtual Machine, and containers. You can imagine that a VM is something that executes machine code, and its environment, so the way it interacts with outside world, is something that looks like a computer. So it pretends to have maybe a PCI bus, and there is a network card sitting on it, and there is a video card, and there is this and that and that. And little by little, we try to strip away all those things because they just added a lot of overhead without any interesting feature. If we contrast with the JVM, for instance, the Java Virtual Machine, what the JVM executes is Java bytecode. It's not Intel or other machine code. And the way it talks to the outside world is using the Java APIs. Now, if we compare that to containers, with containers, we are still executing machine code. And in the case of Docker, we would say, okay, it's going to be Intel 64 bits machine code and nothing else officially. And the environment is the ABI with the Linux syscall interface. That's pretty interesting because those two things, the Intel 64 bits instruction set and the ABI used to talk to the kernel, are extremely stable. They are extremely stable because Intel is not going to change their instruction set overnight because suddenly they would break compatibility with everything, so they don't want to do that. And the Linux kernel syscall interface is also pretty stable because whenever someone changes it, either voluntarily or by mistake, they get an email of, well, list of profanity by Linus Torvald himself about how they're stupid and they should just stop programming and go somewhere and die. So nobody really wants to change that because it kind of hurts to receive that kind of email. So those things are pretty stable, and it means that containers we do today will probably still run in 10 years. Right, from the overhead point of view, containers are just normal processes running on top of a normal kernel. The only thing between a process in a container and a process not in a container is a few labels on top of the process to say this is in container X. But when a process is not in a container, it still has those labels, except the labels say this process is not in a container. But the code path, whenever the container is reading from disk or sending something on the network or doing some computering or whatever, the code path is exactly the same. So the performance will be exactly the same given that you tune the proper things. The context switch between two containers is exactly the same as the context switch between two processes. So that helps a lot for people who want to have bare metal performance. Right. On the other hand, VMs don't have that, but they have a much stronger isolation because VMs are not, well, they are processes running on a kernel, but inside the VM, that's where you do your things. And when you want to get out, you have to go through the number of drivers and the hypervisor, and ultimately that runs on a non-privileged process. So even if there is a critical security issue in your VM and you manage to break out of the VM, you end up being a non-privileged process on the host, and from that point you have to start your attack all over again. It's a little bit like when you're in a prison and you break out of the prison and you realize that you're on the moon and you have to build a ship to get back to Earth. That's pretty much what happens when you can break out of a VM compared to a container where if you can break into the kernel, well, then it's game over because you escalate to the whole machine, and from a security standpoint, that's not cool. So, however, this means that when VMs need to communicate between each other, they have to use the good old TCP IP stack because there is no direct path between VMs. So again, there are some hypervisors that will provide some direct communication path, but this is pretty rare. I don't know of any public cloud that exposed them. And even if they did, they would be different between, for instance, Xen, VMware, KVM, and so on and so on. Like Xen has something like ZenBus, so you can do some really fancy thing and achieve super high performance between VMs, but that's specific to Xen. Containers, on the other hand, can use normal sharing mechanisms. We can use sockets, like local Unix sockets. We can share bits of memory. We can even, like a container, can even see and access the processes of another container directly if you allow that. So that's much easier. And this leads to this kind of comparison. If we were to explain how containers and VMs are different, is that VMs are like brick walls. That's solid. It's pretty hard to knock down a brick wall, except if you're a ninja and you have mad skills like that. But it's pretty slow to build. If you want to move a wall of bricks, it's going to take some time and be pretty messy. However, a container will be a kind of a room divider made of rice paper. So it's pretty easy to set one up. It's pretty easy to move it as well. However, it doesn't provide much security. That's the kind of first thing we think of when we see those. So it's like, okay, containers are not very solid, but at least I can move them around extremely easily, and I can do that with VMs. At the same time, those kind of lines are blurring now. VMs are not exactly those unmovable walls of brick, and containers are not those frail room dividers. There are a few initiatives, like Intel has done something called Clear Containers. There is a PaaS company in France called Clever Cloud that does something pretty similar, and basically they kind of removed things from VMs. They try to look, okay, what happens when we start that VM? Why is it taking so long, as in hundreds of milliseconds as opposed to milliseconds for a container? How can we make those VMs so that they look like container, as in like they would start super fast, they would take a very small amount of memory, and they did it. They made VMs that are not as fast as containers, but they are really getting close. And at the same time, there are people who say, well, we're not happy with the status quo about container and security, so we want to make extremely secure containers. So there is like Giant that I was talking about. They managed to get Linux binaries running on Solaris zones. Solaris zones are extremely secure, and so now you get a way to have secure containers. Another way is to use Linux native security mechanisms like SELinux, AppArmor, GRSec, and then you get something that's also pretty solid. So now if we kind of leave the technical differences and look more about the functional differences. So what are the differences in workflows, in uses? How do we handle containers? How do we handle VMs? So a VM will typically need everything inside it to work, to function properly. You need a full OS, you need a kernel, you will typically have cron and syslog and some backup tools, and well, it's a kind of a self-standing thing. With containers, on the other hand, there has been a lot of things written about machine containers versus application containers. Machine containers are kind of lightweight virtual machines. They have an init process. They run all the usual suspects, SSH, cron, syslog, etc., etc. While application containers will run your application as PID1. If you want to run MySQL, then MySQL is PID1. If you want to run Apache, Apache is PID1, and so on and so forth. Those containers need a lot of help from the outside because they don't have anything fancy for logging, they don't have anything fancy for remote access, and so on and so on. So they need some kind of support from the host environment. The life cycle now. With VMs, the kind of classical approach is you bring up a VM and then it will live, maybe not forever, but at least for a very long time. It will be updated and we will put new versions in it, and that will introduce something called configuration drift. Configuration drift is when I have a server that I deployed 1 month ago and it's supposed to have exactly the same software as a server I deployed a few days ago, but in fact, during that time span, there were some packages that were updated. Maybe the base image that I'm using on Amazon or Linode or Rackspace or whatever has changed a little bit. And so this drift at first is not extremely severe and has minor effects, but over time it gets bigger and bigger until suddenly some stuff works on a machine and not on the other. So to avoid drift, one of the answers is to use configuration management. That's often pretty complicated and that doesn't solve all the problems. So another idea is to use golden images. And with golden images, you might have already heard those either as golden images or Phoenix servers, immutable infrastructure, immutable servers. The idea is that you have templates, you have images for your servers, and when you want to make a change, even if it's one line of code somewhere, even if it's a silly tiny CSS change, then you bake a new image, you start new servers, and you destroy the old servers. So that seems a little bit extreme, but that avoids that configuration drift, that avoids a lot of problems. On the downside, even if that's nice and clean, that's also pretty heavy to set up. And people like typically Netflix and Amazon tell you, we do like this, and it's awesome, it's great, but they have the tooling and the scale, and they can kind of afford to do that. Smaller shops can't always say, okay, sure, we're going to destroy everything and recreate everything each time we change one line of code. It's not always as easy. Containers have this kind of best of both worlds approach where we always create them from an image, but image creation itself is super easy. It's super easy to create new container images, and then it's really easy to switch from the old image to the new image. So why is that? Why is it easy with containers and hard with VMs? It just boils down to the time it takes and how convenient it is to take a snapshot and create a new instance. Like if you've used already like Docker with Docker files, you do that all the time when you build a Docker file. When you have a Docker file with 10 lines, you're creating 10 containers. Each time you're creating a container, you're doing something in it, taking a snapshot, so that's the new image. And then with that image, you're creating a new container, executing the next line of the Docker file, and repeat and repeat and repeat. If you do that on EC2 with VMs and EBS, so you create the VM, then you wait maybe 1 minute or two, and the VM is up. 1 or 2 minutes is not too bad to provision a VM, find the resources, boot it, and everything, but it's still 1 or 2 minutes. It's not like the half a second it takes with a container. And then you do your thing, and then you snapshot the VM, so it's API calls, and you wait for the AWS API to tell you, it's okay, I've done the snapshot of this VM, then you start a new VM with that snapshot. So basically, a build that would take 5 seconds with containers would take probably something like 1 hour with VMs. And that would be for a pretty simple build, not like a super complicated, crazy one. And that's not because VMs are slower or whatever. It's just because the machinery and everything is way more complicated. We have to do API calls instead of, and those calls are slow instead of immediately doing a snapshot and creating a new container. Now let's look at the development process, and we are getting to the meat of the issue here. The best practice when you go like SOA or microservices is you will put your different components on different machines. You will have your web tier, and that's a bunch of VMs. Then you have maybe your API that will be on another bunch of VMs. Your database will be running somewhere else. You have a bunch of workers, that's something else, and so on and so forth. If you want to replicate that in dev, that would mean having 1 VM per component running on your local machine. If you have nice local machines with 32 gigs of RAM, it's kind of okay to have a dozen of VM. However, if you have smaller machines, or if you have kind of pushed the microservice approach to the extreme and you have 200 or 300 components, you certainly don't want to have 200 or 300 VM running on your laptop. So with that means that you will have a significant difference between your prod and dev environment, because in prod you will be running on so many virtual machines, and in dev you will have typically 1 VM and it has a bunch of components inside, but the deployment will obviously be different. In prod, you also need a lot of extra stuff, like you want to ship your logs to Splunk or Papertrail or Loggly or an ELK cluster. In dev, you generally don't want to do that. You just want to have an easy way to check the logs to see what you're doing, but you don't want to have the same heavy machinery. So again, this means very different environments between dev and prod. So with containers, at least we can run many containers on a machine, so we can have the same containers in dev and prod. But how do we provide container variants? So how can we make it so that in production I'm shipping my logs to Splunk, but in dev I'm not running the Splunk collector and all that stuff. I just want logs in the local file and grep and tell and do that to them. So there are a couple of approaches. The first one is kind of bloated containers. So it means you put everything you need in your containers. So you end up with a kind of Frankenstein-esque container that has your application, but also maybe New Relic or Datadog or Splunk or all the things that you need in production. So that's a huge container, and it's supposed to start like many processes. The problem is that the behavior will be different, because locally you just start, let's say, Gunicorn for your Python app, But in prod, you will start many other additional processes, and you can end up with, well, it doesn't work the same way in dev and prod because of those processes, because maybe this monitoring thing is doing something to the app, or it's binding on a port, and so my app can bind to it or whatever. And it also means that it's kind of hard to decouple things, because now in my application container, I also have to put the backup process. Like my ops team told me, you have to install this backup thing and set it up that way and that way. And so it's kind of risky, because as part of my development process, I might break that. And when you break the backups, bad things eventually happen. So the other approach is to use lean containers. And the idea is to stick to this Unix philosophy, do one thing, but do it well. So we stick to one container with whatever you're working on, your component, your code, or your database, or whatever, and then have separate containers for everything else. Logging, monitoring, backups, debugging. So how do I analyze network traffic? How do I check latency? And so on and so on. So how do we do that? The idea is that, as I said earlier, with containers, we can share a lot of things between our containers. We can share files, we can share network stacks, we can even share memory space, and that's what we will use. So for instance, let's look at logging. There are kind of two ways, well, at least two ways to do logging with this lean containers idea in the case of Docker. The first idea is to have your containers write on standard output, and Docker kind of collects these standard output messages, and it will send them either to local JSON files or to syslog. There was in Docker 1.6, I think, the addition of logging drivers, so you can kind of decide where you want to send the fire hose of logs generated by your containers. It's not yet perfect. Like if you decide to send your logs to syslog, then you can't use the docker logs command anymore. But the hooks are there, and down the road, eventually, we know that it will get much better. Meanwhile, another solution, if you have something that insists on writing a bunch of local log files and doesn't want to go to standard output, which is pretty reasonable because most web servers will write like an access log and an error log, for instance. In that case, fine. Let's use something that we call a volume. So if you already know Docker well enough, you're familiar with volumes. Otherwise, volumes are directories that are shared between the host and the container. So it's a kind of mapping, a pass-through between the container and the host file system. So here you can start a container, so that's my application, and I'm telling to Docker, hey, /var/log should be a volume. Make it so, make it happen. So right, when I do that, Docker will allocate a directory somewhere on the host, and it will map it to /var/log in the container. And then I can run another container, and I will use the volumes from option that tells to Docker reuse the same volumes as the first container. And in that container, I will run something like tail-f var log everything. So that's like the simplest way to get the logs out in that case. But if I want, I could just get a shell and manually run tail and grep and awk and whatever I want. If those are HTTP logs, I could have another container in which I install Apache Top, which is a pretty nice tool that kind of gets the HTTP logs as they come, and that gives you the top requests showing up in those logs. So basically, any kind of custom tool that you might need will be in that container instead of being in the application container. So instead of having the application container that ends up being a gigantic garbage bin full of all the tools that everybody that worked on the application installed one after the other, you still have a very simple and lean application container, and everybody has their own little toolbox on the side when they need something. And now when you run in production, you could have a log collector container. So this one could have anything. It could be the Splunk agent. It could be something that tails the log and sends them on RabbitMQ or on Redis PubSub or whatever you want. The application doesn't have to know anything about that. The application just puts the log files on var log, and then that log collector picks the logs in that directory and sends them wherever you want. So that's exactly what I just said. Other upsides are that if you're running some really custom and let's say expensive log analysis, expensive from a CPU or memory point of view, you can isolate that from the application itself. For instance, if you have something that counts unique visitors in log files, that tends to use a lot of memory because you have a pretty big data structure with like the fingerprints of each visitor, like IP address, browser, things like that. Then running that kind of log processing can eat up like tons of memory. And if you're particularly unlucky, you can eat enough memory to take the web server down because the logs will be on the same machine. If you run that in a container, then you only take the log analysis container down instead of taking the web server down. And the last advantage of that system is that if you, at some point you decide to move from one logging system to the other, that's extremely easy to do. You just have to change that logging container instead of changing the application container. So sometimes people ask about what's the performance overhead of this, like because I'm sharing data between two containers, is there a protocol involved, is there some latency, is there anything? No, there is nothing special. When two containers are accessing the same volume, it's exactly just like when two processes are accessing the same directory. So there is nothing special to do, it just works, it's a direct path to the underlying file system, and there is absolutely no overhead when multiple processes are accessing those files. Same thing for synchronization. The data immediately shows up when it's written by your web server, for instance, because it doesn't have to be transferred anywhere else. It's just like when you write to a file, if you read back that file immediately after, the data is here. So it's the same thing here. There is nothing to synchronize because there is really only one copy of the data. Let's talk a little bit about backups. Exactly the same idea. When you want to back up some files, it could be like here I deliberately picked like /var/lib, so those could be database or pretty much anything. Often we have extra tools to ship the files outside of the servers. Maybe we're backing up to S3, so we have S3 CMD or Bodo. Maybe we are backing up through a remote server with SSH. So in that case, we have not only SSH, but also some key material. Maybe we're using rsync or Unison to do like multi-way synchronization. In that case, once again, let's put this data in a volume and let's share that volume with another container. And let's have all those custom programs in the container. That way, and I'm sorry, but I will kind of repeat that to make sure everybody gets the point, but the application container only has what it needs. It only has the application itself, and all those other functions are in separate containers. Right. Another example, when your backup is network-based, so as opposed to I'm taking those files and I'm putting them somewhere, network-based backup here means I'm connecting to the database or to the API and I'm extracting the data, and then once I have that dump or that extract, I put it somewhere else. So it's exactly the same thing. I have a separate container to do that. And the main advantage here is that the responsibility is now kind of split between two teams. There are people working on the application container, and so maybe that's an API, and we want to have something that talks to the API to extract data and save it. Backup kind of thing in the application container. Now it means that it's the responsibility of the people maintaining that container to make sure that the backup script is still running. However, if it's a separate container, then you can say, okay, there are people maintaining that application container, people maintaining that backup data extraction container, and if people working on the app kind of break the backups, well, first, they won't make a mistake like, oh, we accidentally commented out the cron job because it's not their cron job anymore. Now the cron job is elsewhere. Or, oh, we accidentally removed cron, even worse. Or we replaced it with something else. Or, no, now it's something separate. And in addition, instead of having some, let's say, entanglement, because you have that dev team that says this is the container with the API and with the backup script, and then the ops team has to check that everything is fine before kind of green lighting that container for production. Now the dev team can go with that, and separately the ops team will have their backup mechanism, and if something is broken, the step, like it's deployment Wednesday. So for Wednesday, everybody must have everything like in a shippable state. When you move to microservice, instead you can say, well, everybody ships whenever they can or want. We have little separate components. That way, if there is one component that needs to ship like every day, and another that is going a big refactoring, and so for 10 days they won't be able to ship because they are breaking things. With microservices, you completely dodge the issue by deploying separately. So here is the same idea. We apply the microservice framework and ideas to the dev and ops tasks. Another example, let's say you want to do some network analysis. You want to investigate like packet loss or latency or some really weird requests that you don't even dump or ngrep, ntop. If you want to check like number of ongoing connections, you can use netstat or ss. The problem is that you typically end up installing those tools in your servers, and that's exactly like the log analysis problem of earlier. It's like over time, your servers end up having tons of tools with different versions. Like somebody will be investigating something with TCP dump or ngrep, and then when they go to another server, it's like, oh, it's not installed, or worse, it's installed but it's a different version. So I did packet captures from different machines, and then I and it doesn't work because the format are slightly different. That's a nightmare. So here, instead, we can share the network stack between containers. So I start, for instance, an Nginx container, and then I use, so it's Docker run, and the option is --net container, colon, and then a container name or ID. That means run a new container with its own file system, process space, memory, yada yada, but reuse the network stack of that other container. And so when you do TCP dump, you will see traffic showing up on Nginx. If you use SS to see the open sockets and are they like in the exact state, like con wait, wait fin and everything, you will see the sockets of Nginx instead of the sockets of an empty container. Service discovery, that's when it gets really exciting. So Docker can do some linking of containers, which really means DNS injection. And the idea then is that your code just connects to, say, Redis, if you want to connect to a Redis service. And it behaves like, I mean, your container wants Redis to resolve to some IP address. And then exactly that. A DNS entry, which is a fancy word for adding a line into /etc/hosts, so that Redis resolves to some IP address. IP address of another container, or it could be the IP address of a remote Redis service. So the idea is to, in dev, to use Docker Compose to automatically kind of stage that for you. And when moving to production, use something slightly more complicated, but that will, again, not change how the application behaves. So technically, that's the pitch about ambassadors, and you probably have it already, but when you want to link together two containers that are running on different machines, we start container B, so let's say that's Redis, that's the thing we want to talk to on the Docker machine, and then we get the host and port that it's using. Okay, maybe we put that in console or etcd or wherever, and then we start the ambassador that is actually just a relay. It's something that will accept connections and it will just like send back those connections to the actual service. And then we start container A, the one that wants to connect to Redis, besides the ambassador. So we end up with Redis somewhere, and then elsewhere there is my web app that wants to connect to Redis, and just right next to it there is this ambassador that will relay traffic, but also handle discovery, like where is my Redis, and also failover if you want to add that kind of behavior. And the key idea here, it's not to solve a problem, because you still have to deal with load balancing and discovery and failover and all those things, but at least you don't have to do that in your application code. Your application code can to Redis without having to think twice about it, and then that Redis thing is the ambassador that deals with the details. Okay, so again, the idea is to kind of enable separation of concerns. Devs do devs, ops do the network plumbing, and we think that's great. Composition of stacks of containers, and that the last part. So you might have heard about Docker Compose that lets you kind of describe a stack like this. So that's a YAML file, and for each service, you have a section describing how it should be built, should it use an already built image, and so on and so on. And this file can be kind of transformed. So I'm currently working on a workshop about advanced Docker orchestration, and so I use this, that's an actual microservice-based application, and then it's transformed into something like this. This is a kind of close-up on one part of this compose YAML file, where initially I only had the worker and the hasher. And now, in fact, the worker, instead of connecting directly to the hasher, connects to a hasher proxy, and the hasher proxy is an ambassador that connects back to hasher. The idea is that, okay, writing that kind of YAML file manually would be tedious and kind of annoying. However, it's YAML, and the input and the outputs are pretty simple, so it's actually pretty easy to generate that with very simple scripts. So that's one of the, you can expect like this YAML generation and this whole setting up ambassadors and everything to happen automatically down the road. But for now, if you need to do it yourself, that's pretty easy. About Docker and networking, we just cut out Docker 1.7 RC2 yesterday night. So you can expect 1.7 to be like released anytime soon. And among other nice things, Docker 1.7 will add networks as a first-class object, which means that you can define networks, you can put containers on networks, and those networks can span multiple Docker engines, which will give us other ways to connect those containers like that. But even in that scenario, the key idea remains, which is that your application just connects to Redis and doesn't have to know that Redis is actually a local container or maybe an ambassador, or maybe it goes over this new network abstraction or whatever. No, the app doesn't have to know that. The app shouldn't know that. Right, so conclusions. Containers can share more context than VMs. We can share files, we can share network, we can share all those things, and we can use that to decouple complexity. So I like to think of that about just like microservices, but instead of being this is the data layer, this is the API, this is this and this and this, it's more this is the dev team, this is the network team, this is the storage or backup team. So now we have not only multiple components, but also multiple layers of responsibility in the organization, and then can work independently instead of being in lockstep. Like, okay, before going to production, we need the green light from the ops team to make sure we didn't screw up anything. All tasks that used to require VM access can be done in separate containers, and the result is smaller, leaner, simpler containers. And those tags can be expressed as simple YAML files, so that's also simpler than with before. And the kind of the last thing I want to state is that sometimes people think that Docker will solve all their problems because after the first experience, it's like, oh, it builds stuff, it's great, oh, it's amazing, you know, oh, it doesn't do all the things I expect it to do. There is no magic. Docker will not solve all those problems for us, but it will give us really powerful tools to solve those problems more efficiently. So that's not something that would build your IKEA shelf for yourself, but it's a really powerful electric drill so that it's much less hard to do it, if you will. That's it. If you have questions, I think we have about like 10 seconds to answer them.
You had described the network stack. Is that a passive monitoring tab, or can you inject packets into it?
So the network stack, the thing that's upcoming in 1.7, the idea is to first have this kind of concept of networks, and well, by itself, I don't think we want to expose like an API thing so you can inject packets, but if you want to, you just have to start a new container that sits on this network and then will inject packets. Does that make sense?
This was actually the previous example where you were doing a TCP dump or whatnot. I didn't know, was that just for passive monitoring?
So right, you can do both. So for the example I gave with like let's run TCP dump in a container that shares the same, but you can also inject packets. You can do pretty much anything you want. It's exactly as if you were in the same container from the network point of view. It's a different file system. It's a different process table, but it's the same network stack. You see the same interfaces, the same IP address, the same IP tables rule, the same routes, the same everything. But only from a network standpoint. Okay,
thanks. Thanks.
Thank you.
Other announcement. So.
Oh, there we go. Always takes a second. So, a couple of quick reminders here. Well, first of all, thanks. That was for the bits that I was able to see was a great talk. As a lot of them are. About slides. Slides will go up somewhere, either on the speaker's own slide, or we'll host them, and we'll send out, if you're on the mailing list, we will send out an announcement afterwards. We'll also link to them from the event page, so you can all find that. I'm going to give you a couple of seconds, because title TBC is obviously a little bit of a, you can't really make your mind up about that one. That's because Tara got a bit late. Go to the, it's about AWS Lambda, for those of you who've heard about Lambda. Lambda is an event-driven compute service, which takes a different view of whether you should manage your infrastructure at all. It's more like, you give me a problem, I will take care of that for you, very much on an event-based, scalable basis. And basically, Tara will be giving an introduction to AWS Lambda in the room behind us. If you can get online, then you can see it. It's on the program right now. Don't forget, we have one more open spaces session to go at the end of the day. I have cleaned the votes off the stickies that were left. We're all tasked, if you have more questions that come up with the result of this, make another post-it note, put it up on the board. At some point, put your 3 dots on. Everybody has 3 votes for the second round. So yes, I'll just let that flow organically during the coffee breaks or something like that. And then shortly before the second open spaces session, we'll do the same thing. We'll count up. I'll try to count the dots without going crazy. And then we'll pick the 4. We'll do those. And without further ado, let me get in Joe, who's somewhere, and he'll be giving the talk over here.
There he is. Does anyone know whose this is? I think this is one of the speakers who had this little adapter. It's a mini DisplayPort to HDMI. No? Going once? Okay. Well, it'll be here if you change your mind. If you like to walk around,
okay,
you can use one of these.
Okay, yeah, let me.
Which allows you to
Yeah,
walk
let me do
around
that
without
because
worrying
I
to be
pace.
tied up. Are you on HDMI? Okay, you're good. Yep, it's already there. Great. And I'll just keep this here. It's off, but if you have to pass it.
Okay.
Someone. This does not have mute button. Well, maybe it does, but basically on and off is the easiest. It is really loud.
I'll speak softly.
Which one you referring to? This one is not yours. Somebody brought it. Yeah.
Check. Test.
Okay, I guess not as loud. Maybe this one is loud. No. Please don't. Oh, okay. It's a little. Maybe like on the inside. I don't know because it's like kind of a little bit away.
And what we'll do is we'll
Yeah,
turn
that's
it
definitely
towards you.
loud.
Okay.
Very loud.
Better.
I know. Yeah. It has Android as usual in the second row. I don't know if it's the stream issue or it's the code issue, but I think this is a little tweaked. I have
Hmm?
I was gonna say you're
Oh.
prepared to grab it. Yep.
Okay, no rush. It goes to when?
Let's see. Well, I thought Andrew moved it by 5 minutes, but by 10 minutes. Well, according to the schedule, it goes to 3:20.
Okay.
So you have almost an hour. Well, yeah, 50.
Might as well charge my phone.
45 minutes.
Okay.
You need a charger, some on this side.
Ah, good. It's like one.
Or you can use one of those.
Yeah.
They said that there was a dongle that got left in here.
Yes, I
Yeah,
don't know which one it is
this
though.
one.
Yeah, that was.
Oh, that's not me, actually. That's mine.
I remember someone
Thank
pulled
you.
it out. Yeah. The camera angle is set, although streaming is kind of wonky. But if anything comes out of it, so heads up, camera angle is set that it captures the rightmost projector screen up to like about here. I may suggest that switching to a white background might make it more visible. At least in my experience, it's been a little. Yeah, I see. I'm not. I think
No,
it
that
was
was me.
unplugged on
Yeah,
purpose.
I
so that
unplugged it on purpose.
there can be some configs made.
I will in a sec. Right. Is everyone ready to get started? Fantastic. All right. So before I forget, and I don't think about it the whole time, if anyone wants to just find me afterwards, I've got a bunch left for laptops and stuff. All right. So we're going to be talking about containerized data persistence on Mesos with Kafka, MySQL, Cassandra, HDFS, and some other goodies. So before I get started, so who here is familiar with Mesos? I guess after today, maybe at least some folks are familiar. How many folks are using Mesos in production? How many folks are using Kafka in production? All right, cool, great. And if you guys have questions and girls have questions as I'm going through, like let's make this interactive, you know, jump in if it's appropriate, awesome. If not, I'll follow up kind of as we're talking. So my name is Joe Stein, nice to meet everyone. I started a company called Elodina recently. It's a startup focused on supporting open source software. For the last 2 years, we've been kind of out in the marketplace doing consulting, working on some very large implementations, focusing on Mesos, Kafka, HDFS, Cassandra, really implementing and kind of being the glue for companies between open source technologies and their existing data infrastructures. I do some blogs and podcasts online. If anyone's like interested in Hadoop stuff, you know, go check it out. It's allthingshadoop.com. You can find me on Twitter. I actually tweeted out my slides. So if you want the slides right now, just go and pull them off my Twitter. Yeah, that's me. I'm also Apache Kafka committer and PMC member as well, and a bunch of other stuff too. Okay, so we're going to talk about, first we're going to talk a little about file systems, databases, object stores, storage solutions, et cetera. Kind of just talk a little bit about, you know, where the landscape is and kind of what, you know, folks do when it comes to data persistence, right? It's not just databases, there's a lot more involved. We're going to get into Apache Mesos and talk a little bit about Mesos, the architecture, how it works. And then we're going to kind of dive into Kafka. If the fates are well, we'll do a little live demo. And then talk a little bit about Cassandra, MySQL, and HDFS also running on Mesos and how all that works and looks and what the issues are and what you've got to look out for and what have you. Okay, so file systems, right? Everyone knows what a file system is. It's a pretty simple thing, right? You've got you know, space that gets managed. There's directories, file names, metadata, permissions, all this good stuff that kind of goes into a file system, right? It's kind of one of the lowest level primitives of, you know, where you're going to store data or on some file system. Then you also have distributed file systems, right? So we'll just use HDFS as an example as a distributed file system. How many folks are familiar with Hadoop? Oh, wow, that's amazing. Okay, cool. All right, so we don't have to spend too much time then, but let's spend a little time. So the HDFS architecture, right? It's kind of, and many distributed file systems kind of go along this route where they're managing they're managing the blocks remotely, right? So they have some central system in HDFS case, it's the name node that's understanding where the files are actually located within the distributed system. And then it provides streaming data access to be able to get to those files, right? You have all these files splintered out in, you know, hundreds or thousands of servers. You don't necessarily know where they are. So the name node provides kind of that, you know, high-level representation to be able to read and write data as if it was just a file system. And it supports very large data sets, right? You know, a typical file system is going to stop at, you know, how big your server is or how big your disk is, your RAID set. And a distributed file system is going to be able to span multiple servers. There's also replicated log, right? So Kafka is an example of a replicated log. This is another type of persistent system. And in you know, Kafka's case, the replicated log is basically taking in immutable, non-changing data, continuously appending it to the local disk, and then you have the other brokers, the other parts of the system that are going and pulling the data from that leader for the specific partition, right? So if you kind of start to think about, you know, the two things that we've talked about so far, the distributed file system and the replicated log, I'd like to start to get you to have like a mental picture of kind of having all this data distributed on all these different servers, right? Kind of think of it that way. In Kafka's case, we have the replicas pulling data from the different servers, right? So the brokers need to know where the other brokers are to be able to, you know, have this type of coordination. And the durability comes from the replication. Same with HDFS. And then you have traditional transactional ACID type databases. I tried to find a picture on the internet that made this worse than it is, but I think this one will be just fine. And I don't know how many folks have ever set up any type of like MySQL replication or use something like Golden Gate or anything like that. I'm sorry, but that's how you have to make these things durable, right? We're talking about files being located on different systems with potentially thousands of different clients trying in real time. And when there are failures, oh my goodness, what happens? Do I lose my data? How do I get access to it, right? These are all the different type of scenarios that people live with today, right? These are all existing problems that folks have. And then there's systems like Dynamo, right? Cassandra, React, others, where they have a shared nothing architecture, right? So they kind of handle this problem a little bit differently, but they also still have distributed data spread out a lot of different places. You know, in the Dynamo type of solution, you have multiple data centers, right? Where you have clients being able to connect into a single node, and then that node that is being connected to knows where the data is, right? So you have, in Cassandra's case, you've got the coordinator, the client connects to the coordinator knows where the data is able to go reach out to the nodes that have the data, pull it back in, and give it back to the client, right? This is kind of the landscape of where we are when it comes to persisting data, distributed file systems, databases, without getting too much into AP, CP, and that kind of stuff. And then we have storage solutions, and this is also where it kind of starts to get really interesting, is that these storage solutions, you've got storage area networks. They have a place and importance for a lot of reasons, mostly because a lot of folks spent a lot of money on them and they're sitting there. You need to read and write to them. It's important. You also have network attached storage, right? Folks use network attached storage as a way to continuously scale and increase their infrastructure, especially when it comes to things like compliance. You have worm systems. I don't know if folks know what worm systems are. It's, write once, read many, right? This is a big thing in finance and compliance and other industries where, you want to make sure that the data that was written is actually what it was when you come back 9 years later or whatever it is. And then you also have cold storage, right? So there's been a lot of really interesting stuff that's been going on with cold storage, and a lot of new solutions that come out that we're going to kind of get into when you start to take all these different persistent systems and start to apply it to a system like Mesos. It's not just a matter of how do we get the existing system to work on Mesos, but what are the new solutions that we could actually achieve by implementing these technologies together. So we'll talk a little bit about that as well. Any questions so far before we start to like jump out of the airplane, put the parachute on? Anything? No? All right, cool. All right, so quick intro to Mesos. So this is what folks do today. It's static partitioning, right? You basically say, these are my database servers, and these are my web servers. And the DevOps person or whoever it might be sets up DB1 and DB2 and DB3, or they set up the journal nodes, the Hadoop nodes, the data nodes, the Cassandra nodes, the Kafka nodes, and now you've got all these different nodes that are running within your infrastructure. And if you all of a sudden need more resources, then what happens is you start to commingle your resources, right? And everyone knows what a container is here, right? Oh, I can solve this problem with containers. I can isolate, right, my Cassandra nodes from my web servers, and everything will be fine, right? Except when that rack crashes, and then you're kind of out of luck because now, even though you've containerized everything and it's isolated, you don't have any failover, right? There's no recovery. You have to get paged to have someone go put that server back into production. It's kind of a nightmare. And this is kind of when you start zooming out, right? This is more folks' systems look like. This could be a cage, and you've got database servers and Hadoop servers, and they're all kind of commingled within the system. And ultimately, everyone is just overutilized, right? I mean, what is everyone at? 40%, 50% utilization, right? That's kind of the norm, so that if they have failure, they can ramp up or take in spikes. The reality is that when you statically partition, you have all that wasted space, right? All this wasted space and all these different servers come from the lack of properly allocating your server infrastructure for the software. And when you do something with elastic sharing, right, and elastic partitioning, then the computer can figure out what's the best way for the systems to be able to maximize their utilization, right? These servers now are free to either be decommissioned or maybe run other tasks on it. So really, does anyone have any questions about this? This is kind of like really the the meat and potatoes or tofu and quinoa of the of the system. I'm a vegan, sorry, it's one of those things. But this is a really important concept, right? It's the complete underutilization of your infrastructure, and it's not just about saving money, right? It's a lot more than that. Any questions about? So what Mesos is basically an operating system for your data center. The same way that an operating system abstracts the hardware from your software on your laptop, right? You don't have to worry about, when you're programming, you don't have to worry about, oh, what's the IRQ for, my USB port if you just want to do something, right? You have this layer of abstraction, which is called the operating system, that creates that separation. And that's what Mesos does, right? It creates this level of abstraction across all of your servers at once. So when you look at them, you see it as one big giant computer, right? Some of the top 250 supercomputers, at least one, supercomputers in the world are Mesos clusters, right? And basically what you're doing is building a supercomputer that allows you to run anything you want on it, Rails, Hadoop, etc. It presents to the software the underlying components as resources, right? CPU, RAM, hard drive space, etc. We'll talk a little bit more about that in a sec. This is my obligatory slide. I truly believe in Mesos seeing all the things, right? It's the same way that when Linux came out, and everyone got all excited, we could run a real server and real software on it, and it's great. It's open source, right? Mesos is the same thing in my opinion, right? We now have an operating system that allows us to build supercomputers. This is the architecture. So let's quickly go through this so that we can kind of understand a little bit more about how the rest of the systems are going to work in the frameworks. So at the core, you have the Mesos master, and the Mesos master is basically the coordinator for handling all the resource allocation and scheduling between the Mesos slaves and the schedulers. Schedulers are basically intelligent systems that are able to understand the applications that they're launching on Mesos. The applications that they're launching on Mesos, they launch in what's called the executor. And the scheduler and the executor together are called a framework, right? So you have these frameworks that run on Mesos. And a framework could be for any system. You could have a framework for Kafka, a framework for Cassandra, a framework for Hadoop, a framework for MySQL. And what these frameworks will do is they'll have a scheduler that will be intelligent, understanding how to handle things like failure recovery, how to handle specific semantics for that application. And then the executor will launch on the slave node, being able to handle whatever is local to that specific application. And kind of what happens at a little bit lower level here between the scheduler and the slaves and the executors, and kind of how all this is really where all the magic happens. You have this thing called the allocation module. And the allocation module within Mesos, first of all, it's pluggable, which is kind of cool. Second of all, it handles all of the distribution of offers. So an offer comes from a slave, and the slave says something like, hey, I've got 36 gigabytes of RAM and 8 CPU. You want it? And the Mesos master doesn't say anything, because the Mesos master, it doesn't want the resources, but it will go to each scheduler and say, hey, do you want some of this? Do you want some CPU? Do you want some, you want some gigabytes of RAM? And the scheduler decides. Maybe the scheduler doesn't need all 36 gigabytes of RAM and 8 CPU. Maybe it only needs 0.2 CPU and 500 megabytes of RAM because it's running Nagios or whatever, right? So very fine-grained resource allocation is controlled through this system. So the framework, the scheduler says, hey, you know what? These are the resources that I see the resources you offered me. Here's what I would like to launch. And then the master goes and the slave launches within the executor. And then the task for whatever was being launched starts running on the slave. Oops, sorry. All right. Let's keep drilling down. Two components in Mesos that I'd like to talk about. Three, really. We'll talk about the third in a second. So resources and attributes. So resources are really anything on the computer. CPU, RAM. You could actually make anything you want a resource. But for now, we're going to talk about CPU, RAM, and disk space. And then we have attributes. Attributes are basically strings that you set slave that then get passed back up through the master to the scheduler. And this is really important because when let's say you have 1,000 machines and you want to launch, let's say a Hadoop cluster, and it's going to be a 3-node Hadoop cluster, and you've got slave 7, 8, 9 have the data nodes running, and they all reboot. The schedulers need a way to know where that data was originally, right? It's kind of a very intuitive concept, but something that maybe don't get right away. So attributes are a way to be able to tell the scheduler a little bit more about the hardware, right? Is this hardware really something that is for the system that I'm trying to launch, right? Let's say you want JBOD or you want SSD. You could set attributes on the machine to basically tell the schedulers more about that machine and the criteria that's on there, right? Maybe you need a RAID 10 for 14 disk, 15,000 RPM setup, right? It's not just about having a terabyte free of space. You actually have specific criteria. Maybe you want it so that when your persistent services are running, you want them running in different racks, right? If you have 100 nodes, you don't want all 100 nodes running in one rack, because if you lose the rack, they all go down, right? So attributes are basically a way to start to divvy up and separate and give the scheduler the ability to know where to launch its tasks, and do it in a way that is, right now manual, right? Someone will go and say, oh, we need to launch a new XYZ server on rack 1 because the rack 1 server died. Mesos can now do this automatically for us, essentially. So any questions on attributes? All right, let's talk a little about roles. So roles are, excuse me, roles are a way in Mesos to do static reservations. It's basically the way right now to stop starvation from happening, because Mesos will send offers to any framework, not just the one that lost the task. So if you have 20 different frameworks running, and let's say one of those frameworks was for Kafka, and a server goes down and comes back up, the data for Kafka, for that service that went down, is on that server, right? So ideally, you want to be able to launch that application back on that server, right? You don't want to have to stream 2-3 terabytes of data through your network for absolutely no reason. The problem is that if you don't reserve those resources beforehand, when that service comes back up, the master is going to take those resources and potentially send them to other frameworks. So, the server goes down, comes back up, you freed up dozens of CPU and hundreds of gigs of RAM, Spark might get it, Storm might get it, and Kafka might never be able to run another broker on that machine. So there's a primitive called roles that allows us to basically say, okay, I want to set 2 CPU for my infrastructure, kind of like a management NIC. Like in a server, there's the NIC card that no one touches. It's for like the management NIC. You do the same thing with roles, right? You say 2 of my CPUs is for the infrastructure team, and 8 of my CPUs is for data services, and then the other 4 CPUs are for anything else that wants to consume them. And then do the same thing with memory, right? So you could actually go and separate out different pieces of your infrastructure. If you're running on AWS, you could actually set up different cloud formation groups that are for different roles. So let's say you have a Spark job running, and you just want to now maximize more of the Spark job, or you have to have more web servers being able to scale out. You could actually launch your cloud formation templates with roles as well, so you could actually scale out the different parts of your infrastructures without having to affect the other resources. There's a lot of really cool tricks that you can do with roles, but right now it's the only way to do reservations of resources. Not currently. Yeah. Yeah. So right now that's a task in the life cycle of releasing. So one of the things that you kind of have to do is look at your workload pattern for whatever service you have and see how underallocated you are, and squeeze down that top number as much as possible, right? So if you launch a web server with 8 CPU and 50 gigs of RAM, and it only uses 2 and 6 gigs, you have to lower that setting, right? Right now, that's part of the operator knowledge and the life cycle of what is our cluster, what does our allocation patterns look like, and that's what people do, right? And a lot of folks actually can get their allocations like up to above 90%, which is pretty amazing. In one very, very large implementation, I think they're up to like 96 or 97% allocation. Yep. So, yep, yep, you can do that. How you do that though is dependent on how you've done your implementation. So there are schedulers that will actually do. Aurora Scheduler is an example for that. So Aurora Scheduler does preemption. So you can set things like, this is a production task. This way, if a part of the production system goes down, tasks that are not production just get killed off, and Aurora will go and schedule that. You can build an allocator module to do the same thing as well, right? So in the allocator module, you can kind of look at all the tasks that you want and create that type of preemption and priority. There is no current, high-level magical every single task gets a priority, not yet, but you can build the system to be able to do that type of thing. So both quotas, preemption, and priorities. They're all existing implementations that you can look at and either use, right? Like you could use the Aurora Scheduler, or you could see how the Aurora Schedulers implement it, and just implement that yourself. All right, so there's some new features that are coming out in Mesos, which are pretty exciting. Really, the first two for me are the most exciting. Hopefully they'll come out in 0.2.3. So the first is dynamic reservations. So everything I told you about with roles and static assignment for resources, that'll all be dynamic now, moving forward. So when a scheduler launches and it consumes some resources, it could basically say, reserve this. And then the master will not send that resource to anybody else, and it will be kind of, dog-eared for the scheduler that asked it for it to be reserved, right? It's a very, very powerful primitive to making this data persistence be really easy. Right now, it's not complicated, but it's not trivial. So, this feature in 0.2.3 really will make and change the way that folks can run data services on Mesos, because it'll just work without really having to understand a lot of the internals. And then the second is persistent resources for storage services. Long story short, you can basically mount a local path into the sandbox. So let's say you write some data in the people don't know what the Mesos sandbox is, I guess. I haven't brought that up. Yep, okay, cool. So when a Mesos task launches on the slave, they actually get their own little isolated sandbox. And that isolated sandbox, you can go and put and do anything you want in it. You can download the JRE, you could run your own, it's a container, right? The Mesos implementation is all LXC, it's all containerized, it's all isolated. CPUs, they're in C groups, MEMS in C groups, and you've got this little sandbox. And that sandbox is kind of where you do all of your local writes. When the task dies, that sandbox is gone. All right? So if you could imagine in a data persistent world, when you lose a task, your data disappears. Ah! Right? It's a little scary. So you can work around that today, and we'll talk about a little bit of how you can work around that. But this feature basically makes it so you no longer have to work around it. The workaround is pretty simple. I mean, you just write outside the sandbox. It's not that hard. You just agree and have some place on your local file system /mount/dist2/Hadoop. Most people namespace it, so you can run multiple different clusters of things. But that will all go away, and it'll just be a volume that you'll have that you can mount inside of your sandbox, which will be pretty nifty as well. A lot of other things, like if you're using OpenStack or EBS, or have some volume mountable drives, you can take those and mount those in the sandbox. So a lot of cool features. And then another nice primitive that's coming up is add resize task. I don't know or think that'll be in 0.2.3, but I guess we'll see. And basically this is being able to deallocate, it's kind of going to your question, deallocate the resources on demand. So if you launch a server and it has 8 CPU and 36 gigs of RAM, if you want to change that, either lower it or increase it, you have to kill the task. That's not ideal, right? You just want to be able to say, reduce, especially in data persistent services, like anytime you kill something, it's not ideal. So, right, so here you can lower the CPU and lower the RAM without the tasks actually having to die. Again, these are really nice to haves. None of them are required to do all the things that we're about to talk about, but it definitely makes it a lot easier and a lot more fun. All right, so we're going to talk a little bit about Kafka with Mesos. Okay, so Kafka Mesos, our team's been working on this for a long time now. We started using Kafka on Marathon. Marathon is kind of like the initd for Mesos. We started doing that about a year ago. And like 4 or 5 months ago, we started on this path of building a Kafka framework. We're at the point now where and it still says beta. We'll be cutting that over in the next few days, just when we get time to do an official release. This is kind of what the architecture looks like. So you have, here's the Mesos master, right? And then we have, let's say, 2 Mesos slaves. And then we have the Kafka Mesos scheduler and the Kafka Mesos executor, right? So those are the 2 parts of the framework. And then the Kafka Mesos scheduler exposes a REST interface that allows our CLI to hook up to the REST interface as well. And then the executor is basically responsible for managing and launching brokers. So we have an implementation that allows us to schedule brokers on Mesos, right? Mesos will find the place where they go based on attributes or size of the system. And the executors will start the brokers and launch the cluster, essentially. And then once that happens, all of your existing Kafka tasks, creating topics, offset checking, producing, consuming, all of those work exactly like they do today. Nothing is different whatsoever. The difference is that we're now able to make Kafka elastic, right? It's not just set up 3 brokers and they sit there with only, I don't know if anyone's run Kafka brokers in production, but they're not going to necessarily consume all your CPU, right? You have a lot of wasted CPU. So you can run other things on those machines. Here the brokers are isolated, right? So their CPU and RAM will be isolated, and you can give them the disk that they need and make sure that they have the right amount of IOPS that they need to be able to do to write all their data. All right, so when we set out with this, we had a couple of goals. Like, we weren't just trying to build and say, hey, how do we force feed and shove Kafka on Mesos? We really wanted to look at all the operational headaches and trouble that the 30 or so different companies that we have worked with have had. One is the broker ID assignment. I have seen people create broker IDs out of all sorts of things. IP addresses, random numbers, just crazy stuff. And this is a really important thing in Kafka because when a broker goes down, you need to be able to bring another broker back in with the same ID in order for the replication to happen. And if you have an auto-scaling group, it's non-trivial to do that with the auto-scaling group. Basically, if you want to do it, very hacky, but make it work, you have to use the IP address for the broker ID, right? So when you bring the machine back in, you bring in the same IP address, and then the broker ID is the machine. It's really hard to use systems like that. It's very difficult in my opinion. So one thing we wanted to do is make the whole broker ID assignment and that entire process just under the hood and work. Second, we also wanted to make sure that we were able to preserve broker placement so that if brokers did fail, they would be able to restart in place to exactly where the data was. And we also wanted to be able to do config changes on the fly. So many times you've got to go in, especially when you're building up a new Kafka cluster, and you just want to change some configurations. If you have 20 nodes, there's no reason to go and run Puppet or Chef and then restart all the servers. I mean, it really is a pain. So we really wanted to ease the administrative burden for configuring Kafka and doing things like rolling restarts. We also wanted to make the brokers be able to scale up and scale down automatically. And the scaling up and scaling down automatically, like really making these brokers elastic, is not so much just about in load coming in and like if you look at a utilization curve, right? When the sun's above the Pacific Ocean, your traffic's at the lowest, right? We wanted to make sure that we could shut Kafka brokers down so that the resources the Kafka brokers were using could be used by other people. Right? We really wanted to be good citizens, that if the Kafka brokers weren't needed, right? Maybe you need more brokers on Black Friday if you're an e-commerce business. Fantastic. Hit a button, scale them up, use them. And when you're done, hit a button, scale them down, or have a programmatic way to be able to do that. And then we also wanted to do some other smart partition assignment and a bunch of other stuff as well. So these were really all the goals that we set out with and are all part of the existing implementation. All right, so quick a little bit about the scheduler and the executor. So the scheduler is going to provide us all the operational automation for the Kafka cluster. It's kind of like the the brains of the operation, right? So every scheduler in Mesos really understands the system that it's launching and it's working with, how it handles failure scenarios and everything else. Our scheduler also exposes the REST API and CLI, which we'll look at in a second, to do everything that you need to do, essentially. And you can run it on Marathon for high availability. This way, if the scheduler goes down, no big deal. Another one starts up, and the whole cluster doesn't have any downtime. The executor is pretty dumb. It just runs the Kafka broker and then talks to Mesos and the broker and handles the restarts and the controlled shutdowns. Very, very simple part of the system. Also to note that the Kafka Mesos framework will run any version of Kafka. So if you use the Confluent version, awesome, it'll work. If you're still using 0811, that'll work as well. If you want to roll your own version of Kafka and apply a patch or put something else in there, like different metrics, you can do that as well. So it just takes any Kafka binary and we'll run that broker, essentially. It's really good for testing as well. All right, so the CLI and REST API. We really wanted to make sure that the administration of the system was just dead simple and really easy for folks. So the scheduler, so you can start the scheduler, and then you have the ability to add brokers. So hopefully the fates will be willing and do a little demo here. You can go ahead and add brokers. You can update resources, right? So this is not just CPU and RAM, but these are also things like configurations as well. Let's say you want to change like the log retention bytes. You can go ahead and just do that from the CLI and stop and start all of your brokers. It's very, very, very simple. You could also just take brokers out if you need to take brokers out. We also have some nifty rebalancing features, and then a whole bunch of other stuff that you can see just from the help. And everything that we have in the CLI is also exposed through REST API. So any programmatic access that you can do manually, anything that you can do manually can be done programmatically with REST requests. And it's really simple to launch brokers. Let's see if we can go ahead and do that. Can everyone see? All right, so I'm going to start the scheduler. And that's it, right? So the scheduler starts. We'll make sure that we see resources coming in. All right, cool. So we see that we've got, you know, a little over half a dozen CPU, almost 10 gigs of RAM, a whole bunch of disk space, and some ports, right? So these are the offers that are coming into the scheduler saying, hey, I've got resources for you. So let's go ahead and, all right, so we're going to launch, we'll add 3 brokers. So by adding the brokers, we're just telling the cluster these are the brokers that actually need to be there. So we'll go ahead and add 3 brokers. That's it, they've been added. And now we can go ahead and start the brokers. Click here. Cool. All right, so it takes a couple seconds. But I mean, if you can imagine, like, you know, someone said to you, oh, I want you to stand up a Kafka cluster. It's going to take a little bit longer than this just took. So, and that's it. Oh, I guess I launched 4 brokers. I forgot. There you go. So we've launched 4 brokers. And that's it. These are now 4 Kafka brokers running just as you would expect them running and working today. And if you want to know where they are so that you can go ahead and, you know, work with them, just go ahead and do a status. Could also be curled. Right, so you can get a JSON, so your software can get this information. And here's your service discovery, right? Here's your broker endpoint running on different ports, and you can go ahead and start producing and consuming from Kafka, just like you do, exactly like you do today. And when all of a sudden you need to launch another node, pretty simple. Let's go ahead and Let's see. Go ahead and launch a couple more nodes here. Let's say we just want to do one more. So go ahead and add one more node. And start it up. And let's say we decide that 0.1 CPU is just not enough, right? That's fine. We can go ahead and run the same updates, make changes to the cluster. Very, very simple operations. I'm going to keep going. Jump to some other systems quick. All right, so let's talk Cassandra with Mesos. All right, so there is a Cassandra framework for Mesos, which has just recently been released that gives you all the goodness that you get from Cassandra running on top of Mesos. So you can go ahead and check that out. There's a scheduler. The scheduler, like the Kafka scheduler, is very intelligent. It understands everything that it needs to know about Cassandra. It understands the concept of the rings and the nodes and how to deal with failures. It understands that maybe when you, just like the Kafka scheduler, that when a node fails, you don't necessarily want to start that node somewhere else right away, that you want to wait a little while and see if the slave recovery has happened before you just go ahead and move terabytes of data across the network. So the Cassandra scheduler is, a lot of work's gone into it, and it's really getting there. It's pretty cool. And then the executor understands a lot more about the specific Cassandra node that it's operating on. It's able to interrogate it, pass that information back up to the scheduler for people to access and monitor it. And then HDFS on Mesos. This is, to me, very exciting, right? Being able to launch a distributed file system on Mesos is awesome. For me, the most exciting thing is being able to create a cluster, put a petabyte of data on the cluster, and then shut it down. Because you don't need to access it. And then when you do need to access it, turn it back on, right? So there's a lot of really cool solutions that you can get into when you start thinking about what does it look like putting a distributed file system on Mesos? Like, what do I actually get from it? There's a lot of stuff that you can get from it. So this is a very exciting part of the ecosystem, at least for me. And then there's MySQL with Apache Mesos. So MySQL at Mesos, this came out of Twitter. So Twitter open sourced it. It's on its way incubating with Apache. The vote passed, so it will be an incubated project. But you can check it out now. It makes it crazy to go ahead and launch a MySQL cluster. Just a couple buttons, and then all of a sudden, just boom, just your MySQL cluster is launched and running, and now you can go ahead and just insert and select your heart's desire. They did a really great job with it, and it's written in Python, which is cool too. Okay, before I get kicked off stage, because I think we only got a couple minutes left, does anyone have any questions? Yep. The question was, how does the mashing between the offers and tasks happen? I'm not sure what you mean by mashing. Yep. So yeah. So the slave sends the offers through the master to the scheduler. The scheduler says, "Hey, I have a task that I want to launch." Sees if the offer is less than or equal to what it wants, and then requests that to happen. Essentially, it requests the launching to happen, and then the slave gets the mandate to start the executor with those resources, assuming that it's there and it's not, hasn't crashed or whatever. And then the task launches based on the resources that the scheduler said to launch with, which is not necessarily what the resource offer was, right? If you're the scheduler and you need 1 CPU and a gig of RAM, and I send you an offer for 2 CPUs and 5 gigs of RAM, that's great for you, right? You could launch on my machine, essentially. I don't know if that answers your question or not, but. So the attributes, the scheduler gets to see the attributes, right? So the attributes are just strings that get passed through. The master doesn't really look at them at all. But when you get them in the scheduler, you're able to see the attributes, and you can build software that can now, because don't forget, the scheduler is a single piece of code, right? So we could actually see all the different offers that are coming in, what are all the different statuses of all the different pieces that are running. what are the attributes on those? So the attributes are in the resources, right? And it can actually look at that and make whatever intelligence to when deciding whether or not it should accept an offer, right? So like if a, like I said, when a slave goes down, you may want to be able to just, you know, it went down, alert saying the backplane crashed, and you don't want to wait the 10 minutes that the scheduler is going to wait. So you can change the constraint, right? So there's two parts, there's the attribute and the constraint. The attribute comes up through the task to the scheduler, and then there's the constraint that says, how do I want to apply my tasks to that attribute, right? Do I want to say, you know, unique host name, meaning this task will there will only be one running on every machine, ever. Or do I want to cluster by rack, which means if you have 3 racks, it'll put the task 1, task 2, task 3, task 4, task 5, task 6, right? So you have a lot of different ways to control the constraints on where the tasks end up based on the attributes. If you want to know more about that, the Marathon documentation is great for that. We use the Marathon constraints in Kafka, and I think most people end up using them. They're really great. Check that out. Yep. I kind of feel like it does that already. So question. So the schedulers themselves, I mean, you can have thousands of different, you know, executors running on a slave, all doing different things, all with different workload patterns, right? You could have your, you know, MySQL, Kafka, web servers, you know, all in separate containers running on that machine, essentially. Yeah, it does that from that perspective, but it doesn't do it from the VM perspective. It does it from the container perspective, right? All in C groups, all in the kernel. Sure. Yeah. Yeah, so we do some Docker stuff on Mesos. You can take the schedulers and run them as I would advise to maybe not do that with the executors and the tasks. There's a couple of, you know, at least in my opinion, there's a few little alleyways that you have to contend with Docker in production. The number one is that the daemon, when the daemon dies, all your tasks die. And that's very anti-Mesos, in my opinion, right? When you have tasks running in Mesos, if this Mesos slave process dies, your tasks still run, which is huge when you're trying to do an upgrade. Imagine you have a fleet of servers and you're trying to do a rolling update. When you do a rolling update of your software, you don't want every single task to fail, right? So let's say you want to upgrade Mesos, all your tasks still keep running. If you want to upgrade your Docker version, you have to kill your tasks to upgrade your Docker version. Like, to me, until that gets fixed, I have a lot of issues putting persistent data and even some other type of data in Docker in production, just from that perspective. That's yeah, that's my opinion. But it's still great. Besides that, it still has a lot of usefulness, right? Like, if you're okay with willy-nilly and it's, you know, you're fine with that, maybe a web server or some other system or whatever it is, it's fine. It's good in testing and development. You know, and as long as you know what you're getting into, then it's okay, right? As long as you know that when you upgrade the machine, everything's going to fail, just don't upgrade your Docker version, and then that won't happen, right? So there's a lot of different ways to contend with that. If you're willing to take the trade-off of it, it's worth it. But you have to know what the trade-off is, and that's the trade-off, essentially. Yeah. I prefer rather not to say, and that's okay. Yeah, I mean, there are quite a lot of like mind-numbing Mesos implementations that are out there. Like I said, like in the top 250 supercomputer size, it's quite incredible. Yeah, it's kind of also nice when you just get like 5,000 CPU to do anything that you want, and then every developer could have thousands of CPU and hundreds of gigs and even terabytes of RAM just isolated for their own tasks, right? I could be working which is completely different than your Hadoop cluster, and we're running on the same, you know, infrastructure, right? You don't just, all of this is isolated and separated. You just run multiple clusters, right? You want your own Kafka brokers? No problem. Spin them up. 2 seconds later, have your own Kafka brokers, whether it's in development, testing, or even in production. You know, all of that becomes very fluid and very simple for folks. And it spins up very fast too. Right? It's a container, right? It's not a VM that takes minutes and days to boot and then crash, and then boot again, then crash. Right? The container it just runs. I think I'm getting kicked out. Nope. All right. Does anyone have any more questions? Yeah.
Process of integrating the existing have Mesos manage.
So Mesos does the containerization for you on launch. You don't have. There is a little bit of effort that you have to do to get it so that it launches, but you don't have to. You just have to put it into a tarball, and then the executor downloads the tarball and then runs it, and it runs it in a container. There's not a lot to it, and it's great. So the systems like Marathon. So Marathon is a system that can just start and stop services. Let's say you have a web server or web application, or even like Node.js. You can have all of that download into the sandbox and start, and it starts in the container. There's no pre-packaging that you have to do except to zip it up. Sure. Yeah, you will have to do some work to get it so that you can have all your dependencies packaged in that one piece. And then in cases like that, it may make more sense to take the trade-off and put it into Docker. Because if it's such a complex dependency that you've got to do all this testing, it may be best to test it into a Docker container and then just launch the Docker container on Mesos.
So all those folds got to be Dockerizable, but not Dockerizable.
I mean, that's a good way to go about it. I think that's a fair, try to make it Dockerizable, and you can get the benefit without Docker. And then if when you do need it, you can use it. After you do it a couple times, it actually becomes pretty simple. You kind of get used to, what are the piece parts involved to do that. Once you start downloading your JRE and running it locally, you just keep doing it. Right? Once you've done it once, you're able to, reuse and do it again, essentially. Any other questions? Anyone want Kafka stickers? Yeah, I will be around for a while, so you can come catch me.
So just before you all go, it's coffee break time now. Obviously, thank you very much. Yeah, my bad. Just a little too quick. Abusing my white shirt privilege. We're back in here after the coffee break, and then we will split. We do the same thing again. We'll have one session just for 5 minutes in here, and then we'll split the remaining for the last talk. Don't forget,
Did you have a white shirt? I'll
open
give you two.
spaces. Either vote.
You guys
Vote on the existing ones or put out your own.
Yeah.
So the multi-tenancy question I asked is more from the control plane perspective.
Okay.
So for example, if a service provider can deploy Mesos to manage like multiple tenant related
So I
infrastructure.
understand. So you're talking about things like isolated networking,
Isolated networking, isolated scheduling to specific nodes where, say for example, a container in a containerized fashion run a specific set of physical nodes.
So the networking story is not as good as it should be yet. It's being worked on. But the second question is completely possible. So you can take things that need to be data locale aware and cluster them together. So let's say you're running some database like HBase on top of the HDFS. You want your region servers to run on the same machines that your data nodes run on. That's kind of the question you're asking, right?
No, this is more like, say if I'm a service provider, I want to host do resource allocation for multiple tenants on a set of physical infrastructure. So is it possible to have Mesos deployment?
So
for multiple tenants,
not without a lot of coding.
That's what
not without a lot of coding. I mean, at that on like OpenStack and then put Mesos on OpenStack, which you can do. So Cisco Cloud has an implementation that allows you to install very easily Mesos on OpenStack to do that kind of stuff.
So a single OpenStack deployment could serve multiple tenants.
Sure. And then each of the different customers could have the different Mesos clusters. And then if you wanted to do routing between them for whatever reason, then you could use Neuron or Neutron or whatever they call it. to do that kind of stuff,
Oh,
right?
okay.
But that doesn't exist now in Mesos. So some of the work that we're doing now, the Cisco, Mesosphere, a couple of others, Basho, is to improve the way that networking actually works.
Right, yeah, we record and, well, actually, we stream on YouTube records. This
Oh, so you
room
guys are
is-
streaming.
Yeah, this room is not as reliable, we're having some trouble here. The other room is good though, because we have our own camera and it's working out better.
Okay.
But this whole system is like, this is supposed to work, I cannot do it here. Like, I'm supposed to be able to change camera angle, change the way that this,
All right. People are slowly filing in, which is good. Gives me a second before we give Ben from VM Turbo some time to talk about what they do. Sorry about the cold coffee. Yeah, we're out of. It doesn't really matter. That's our way of saying don't drink it. Yeah, they recycled the whole 10,000 cups that we had, so now they're recycling. Anyway, what happens now? Same kind of as last time. Everybody's in here for 2.5 minutes or so, and then we have 2 more sessions. And then we have the last open spaces. So when you get out of the next session, if you haven't voted yet, please vote. We'll tally up the votes. Then we have an open spaces until the end. If you're planning to come out to the drinks this evening, don't run away after the open spaces is closed. I'll come around, give people about 5 minutes, because we will be handing out the drinks tickets. And then you can follow a pod of people going toward the Cambridge. If you've got the Friday sheet, it has directions on the back. Over to Ben.
Great. Thank you very much. I'm Ben Yamini from VM Turbo. Before I tell you just 2 minutes about VM Turbo, anybody here ever heard about VM Turbo before today? All right, a couple. Anybody ever use VM Turbo? Okay. So we are one of the fastest growing companies in the cloud and virtualization management space. We're headquartered right across the street. We're up to about 400 employees, about 1,000 customers, 30,000 users worldwide. We're a startup. We were started in 2009. And what's driving a lot of this growth is something you guys are all familiar with, right? So the data center has evolved quite a bit over the last 20 years. We've moved N-tier and virtualization. Today, a lot of the talk is about web scale, running on a public cloud, and we're seeing more and more companies building these distributed applications and a need and ability to control where those applications or where those workloads run to assure performance. So companies like Google that are running web scale, right, so they are not using manual processes to make decisions of where to run workloads, when to start them, when to stop them, what configuration changes to make. They are using a completely algorithmic approach to making those decisions. And I think the simplest way to describe VM Turbo is that's exactly what we do in your data center. It's a lightweight image. It drops into any data center, and then it makes decisions on where to run those workloads, under what configurations, how much CPU, how much memory to give them, whenever whatever host to run them on, whatever data store to associate them with, all with the goal of assuring performance of those applications. The other side benefit of this is when you do this, workloads get only the resources they need. So what happens is you're running your applications on the least amount of infrastructure. That helps application owners spend less time worrying about availability. It helps developers be more efficient. It also helps you spend less time and money on infrastructure, more time on development. Last thing I'll say, we are hiring. We're hiring in sales. We're hiring in marketing. We're hiring in engineering. So if you've got questions, please come by and find out more. That's it.
Now, yes, you've got 2 choices. Another tough one, either here, for Igor, or Barak, over in the other room.
So what? That's I see. Yeah, he switched. second with on any basically Linux machine for some reason, as far as I've noticed. Okay. Also, this thing is kind of wonky, so we want to make it straight. Curious. Ah, here we go. Yep. Okay, you got it.
You guys hear me? Yep. Awesome. Hands. Who is awesome? I like it. Who is right now working on breaking their big monolith code into like microservices? Else on the monolith or on the microservice already? Okay. Who has problems running microservices in production? Okay. So if you don't have problems, you can leave. Right? Okay. So I'm going to show what we've learned going through all of those stages, breaking, migrating the old code into microservice using Docker. Sorry? I'll get to that. First, I'll just want to touch a little bit on the interesting story. I heard an adaptation of an old story to the modern world. A guy finds a genie bottle, and genie pops up and says, "Okay, you have one wish." The guy says, "You know what? Like, I hate flying. I hate being, but I've never been to Hawaii. I want to go to Hawaii. Please build me a highway to Hawaii." So genie says, "Like, are you crazy? You know, like how much it costs? You know how hard it is to put those like columns into the ocean floor? How hard? Like, what's the environmental impact? We're going to kill a lot of species. You're crazy. You have another wish. Try something else." So the guy says, "You know what? Like, we're right now breaking our monoliths into microservices, and we're trying to run the production. There are a lot of problems. We need some help." So Ginny scratches his head and says, "Like, you know what? What do you have in mind? One way or two-way highway?" Right. So that's more or less where we've been, but it's coming. It's getting easier and easier every day. I'm going to walk you through like what we've learned dealing with all of those issues. So I'm going to tell you a story today about cheese, but this is not actually about like I love cheese, I love like all kinds of cheese, but we're not going to talk about not the like real cheese, but about the story written by Spencer Johnson about dealing with change in business and life. It's a great story. You should like everyone needs to know about this story. So why I'm talking about this? So I've worked. Like, my name is Igor Muchnik, and I worked with or for a couple of like pretty big companies. And almost in every company, we had the same, more or less the same repeating story. Like big code, legacy code, make it work now, right? So we've accumulated a lot of interesting ways of dealing with those problems. And actually, since today, I'm back in consulting because I want to share with other people all the learnings that we've acquired. So when I'm saying we, it's kind of like an amalgamation across like multiple different companies. So across the last 2 years, I worked back 2.5 years and consulted for a couple, like advised for a couple of other companies. So when I'm saying we, it's across all those different projects that we've been running. So the story starts with organization. There are a lot of cheese sitting in one single place, and the business is getting used to that. There are a lot of stuff. It's very well known. Big monolithic code, legacy app. It's sitting. Everybody's happy. Developers are happy as well. They can load the whole code into their development environment, put breakpoints. It all sounds nice. And having cheese makes you happy. The business gets used to that. The business is humming. Everybody's happy. The infrastructure is known. Everything is known. We know how to deal with change. We update code. We schedule downtime. Everything is nice. But like more and more change starts to come, and we're starting to go because the more important cheese to you, the more you want to hold on to it. You don't want to introduce a lot of change in the infrastructure because it makes you unstable, unhappy. So we're putting a lot of like approvals in place, change requests, maintenance requests, like tickets, and we start to guard it. But the paradigm shift is happening, right? The business starts to feel the pressure from the markets. The business needs to react faster and faster to the change. So they're starting to put pressure on the development and the systems organization, operational organizations, to adopt more and more, to react faster and faster to the change. And we're starting to see the shifts from stable environments to more like reacting to customer requirements, like making customer happy. We're starting to see shifts from the waterfall to agile, and the infrastructure and the operations, they starting to struggle how to react to that. But if you, the business understand that if you don't change, you can become extinct. So we're starting to see slowly the operational teams and systems teams start to adopt virtualization and starts to think about clouds, starting to bring their private cloud to public clouds. And this new things pops up, like, and getting sort of excited, but still don't know what to do with that, right? There's a lot of talk about, is it like yet another virtualization? Is it hype? What's happening? But then the interesting things happening. So if you can see the trends of the adoption, virtualization compared to containers, right? This is graphs taken from Google Analytics on the interest on different topics. So you can see that virtualization hype happened kind of like within 5 years, and the Docker surpassed the rate within 2 years. Am I going to explode here? Okay, cool. So the adoption rate starts to grow very, very quickly, and the organization, a lot of organizations starts to think about maybe there's something, and everybody starts to think about like how to adopt it. And everybody starts usually slow. Okay, let's figure out what to do with that. Maybe the very, very first thing we'll do, we'll start isolating our builds. Because usually when we have a build server, we need to install like a lot of dev tools there, keep it always stable because it's becoming very important to our release cycle. That's where almost every company that I observed over the last couple of years, that's where everybody starts. Using Docker plugins, for example, with Jenkins, starting to get very nice stable builds, build environments, everything is controlled, everything is nice, but it became, in the organization, starting to adopt very, very high velocity release cycles. It didn't really work because it was time to bring this new development environment, the new build environment into the, they're starting to be cached. But then you release a new version of that and it's like cycles begin. So it didn't really work. A lot of issues becoming also like a lot of like companies starts to figure out like how to deal with the Docker hosts and how to deal with the network storage for those containers, and we'll get to that in a second. As soon as the company starts to learn about the containers and how they work and they understand their limits, then we're starting to see that team starts to embrace it. And it's like really becomes very, very excited. Everybody gets very around that. And we immediately, this is very well correlates with the shift to microservices. So we see the speed of the deployments starts to grow, and the requirements for the increase of speeds of deployment starts to grow. So before that, we had data centers where deployments were, each server was different. It, like barely anybody knew how it got to that state. Then we started to move to virtualization. With virtualization, we figured that we can have images, we can have the process repeatable, and the deploys that went into those virtual machines, they were staying a little bit, the life cycles of them, they started to shrink, like to weeks and months. Now with high velocity releases, like in the very well cultured organization that adopt DevOps and like short iterations, we're starting to see that the release cycles, they're shrinking to multiple times a day. It's very, very common, right? So the speed of bringing up virtual machines is not good enough because developers, they want to try and test their code on very, very, very short iterations. And this is where containers actually started to shine. But then everybody starts to ask a question. So if we work on application, then what actual application is for us? Is it a single container? So everything that we had in the virtual machine, why don't we pack it up into container and just deploy it as it is? We can enjoy all the benefits that container bring, right? But then how are we going to maintain it? Like different components inside that container start to change, so we need to release a new version of container again and again and again. So that doesn't really quite work. And our Docker guidelines suggest to think about single responsibility, where create a container for each different functionality. Like if you need, like more or less one per process, or if you need a tool or a test tool, put it in its own container, and then use composition, put them together. So then we starting to hit the limits where a Docker ecosystem doesn't really quite work. There are a lot of missing gaps there, and we started to see a lot of tools like Fig, and now it's called like Docker Compose. They start to pop up here and there and start to get proliferation. But then different frameworks, different tools, different systems, they didn't really know how to deal with that. Now we're starting to see more and more systems implement that notion in their ecosystem. For example, Kubernetes, they call it pods. A pod is a composition of the container that can be collocated in one machine. They have to be collocated in one machine. In Amazon ECS, we here they call it task, which is, to my taste, it's a little bit misused, maybe like overused term in here. But then if we have an application as a composition of containers, in many cases microservices, actually we need like a bunch of those applications work together. So we're starting to get into a graph of containers that can be spanning across multiple machines. And this is where a lot of issues right now happening, and very little existing systems that know how to work with Docker and container virtualization, they totally lacking any functionality in that space. And we'll talk about this, how we solved it. But really about containers is that allowed us to create immutable artifacts. A configuration management, which we really, really love, and we got used to that, has some issues with the drift. Because many cases, if you keep a server up and running for a long time, the changes, they accumulate. And there is happening in drift. If you copy the files, if you next iteration don't need that file anymore, you need to figure out how to take those files away. So have you guys experienced the configuration management drift? Yeah. So I think everybody likes, like, after we get excited about configuration management, we start to learn about this, we're starting to see that. And then then you start to think about, if we're running on the private cloud or private data centers, how can we make sure that those servers, they don't experience the drift? So we need to figure out how we rebuild them constantly and very, very often. But this is where containers are awesome, because when it got dirty, you kill it, you bring a new one up, and you kind of back at the beginning state. So on the other hand, when you're starting to work with, like start to move, let's say, to DevOps route, to hear things where you need to version everything. And containers are like awesome at that. Configuration management doesn't really, if you specifically do it wrong, like a monolithic configuration management, where everybody starts, where one repo represents the center, it starts to be very, very hard to say what actually specific configuration at any moment in time of any server, right? So you need to think about how to separate each configuration management of each server separately, right? So there are a lot of ways to do that. If you're using Chef, for example, you can use Bergshelf, Puppet, if you're using a Puppet librarian. So there are ways to do that. But Docker makes it very, very easy. So we started in that place, but we very, very quickly saw that the release process itself started to not only drift, but accumulate a lot of knowledge about how the artifacts move through the process end to end. So we even got to the place where we brought a tool that allows us to version the whole release end to end. And we open sourced it. You guys, you can, I will not get into that. But so we got to the point where everything is versioned. Servers, containers, release process, the code. And it got us to this, got us to about how we're going to deal with the whole release process in the new light when the Docker comes in. So the usual release process we end up with where developers commit code into repo. It keeps storage. A lot of different artifact storage we use. The one that I really like Artifactory. It's really great. As soon as the artifact is created, this artifact is saved along with extra metadata that we'll talk a little bit later why we need that. That talks about not only the version of the artifact, but like what's the contract, what the contract versions, what's the dependencies in need, what's the dependency of the contract version dependencies need. So that allows us to track its dependency. And we'll talk about this a couple of slides later. As soon as the artifact is created, the next step kicks in, which bakes a Docker container. So Docker container, after it's created, is versioned with the same version as the artifact itself. And it's uploaded to Docker registry. Different types right now of Docker registries. You need to think about which one you choose. You can deploy your own on your local data center if you're worried about privacy. But you can use Docker Hub as well. And they also provide you private repos. But you need to think about like what would be the time for you to bring this artifact back to your data center. So Artifactory recently, they released a new version that also works as a Docker registry. So it was really played well for us. And then it goes into deployment. So there, let's talk about, skipped the slide. So let's talk about the challenges that we had with the Docker registry. So when you start to talk about Docker registry, you need to keep in mind a couple different things. Who can access those containers? Who is allowed to change containers? Who is allowed to upload new containers? And after you solve that, you need to think about how to keep that registry all the time, because it's become very, very quickly, since Docker creates extra containers, it's very, very quickly starts to consume. So the storage is cheap, but you need to make sure that you actually give attention to manage that storage. And if you go back to my point when I said that the artifact has a bunch of metadata, so we started to use that to make decision what containers or what artifacts to prune from the artifact storage and the registry, because otherwise it's becoming totally unmanageable. The sizes just grow very, very rapidly. But since each artifact is hard versioned, even if we prune the artifact that we still need, we can always recreate it from scratch to exactly the same point. So after we solve those problems and we manage our registry and we put the artifact in the registry and the Docker into the registry, Docker container, then we need to go into deployment. And this is more or less, we knew how to deal with that. We still go back into our well-known configuration management where we use it to configure Docker hosts. They don't change that much. Only they change with the speed when Docker releases new versions of their product. So as soon as the Docker host is available for us, the orchestration pulls in the Docker container and starts it. But this is where we started to run a lot of different interesting issues, because we need to figure out at the beginning what the application is. And we ended up with a place where application is not one container. Application is a composition of the containers. So when Docker starts, Docker itself out of the box doesn't know how to launch the composition container. You just need to launch those containers one by one. So you need to have a mechanism that knows how to compose them together, right? We looked at Fig. We started to use Fig. But then we ran very, very quickly into the problem that the time of starting of the container and application side of the container takes a little bit time. And then when the services starts to find, like, want to find each other. They actually can't immediately, and they start to fail. We start to run the problems where containers needed to be initialized with different settings based on the environment settings, maybe secrets, different certificates. And Fig and Docker Compose till today, they still don't know how to deal with that. So all that. And we started obviously to write our own. We also figured out, which is today is more or less known, when you build containers, as much as possible, remove any settings from those containers and make them external. Because otherwise, you will need to make different containers for different environments, for developers, for production, for testing environments. So this is a big point here. Do not bake any settings. Make containers as generic as possible, and use the external and ideally hierarchical configuration settings management systems. So we a couple places we use Console, a couple places we use Zookeeper or Hiera. There are a bunch of others that you can use, right? But this is important. And talking about secrets, you need to think about and talk with your security teams how those secrets will be ending up inside the containers, how they will be provided to your services that's running. And just to keep in mind, environment variables, they're visible if you do Docker PS. They pop up on your screen. So if that is, your security team will tell you, like, no, think about maybe you'll give those secrets through maybe like mounting different partitions or volumes, or maybe keep those secrets in different containers and ship them from different places. So it's very, very important was to start thinking about secret management. And we use a couple of other systems, like, again, like Console or etcd, to manage our secrets. But then we started to run into another problem. We started to experience container sprawl. Creating containers is very, very simple. And we started to get millions of them, literally, all over the place, everywhere. And we different questions, like, what do we actually need to have this container running, or it's still some shred from the previous orchestration that wasn't cleaned up? Who actually the owner of this container? And it's not only containers that's running on a Docker host, but also containers inside our registries. So what to deal with that? There are like a ton of them, and like a ton of different versions. And you start kind of like starting to lose there. And in many cases, all those containers, when they previous version of Docker, and still today we see that when the container, Docker says it launched the container disappears. So it may be like either crashed internally or Docker didn't handle it correctly. So there is still some issues there. So keep in mind that you need a very good eye on those things. But also we started to see a lot of containers that we see them as operational, but nothing happening inside the container. So we call them zombie containers. What to do with that? Not always you know if this container is actually doing something or it's just like sitting around and doing nothing. So after we solved that, to a certain degree, we also started to ask questions. Okay, so we know how to build the containers, we know how to start the containers, but how are we going to test that? And this is, in many cases, this is a separate discussion about like start to think about microservices. You needed a very, very good to put a lot of thinking how you're going to do that. A lot of ways to do that. But what we learned about Docker is that the way how we start containers in production, they're way different from the way how we start containers in the development environment. In many cases, developers, they're really, really excited about Docker because they can run like almost the whole environment, or actually a big chunk of the environment, in their development machine. The containers are very, very lightweight. This is great. But we also want to make sure that developers, they test the containers or application or the environment in the same way how it will be running production. So we want to make it as close to production as possible. And this is where we started to run into some kind of like split brain. So we want to be close to production, but we actually can't do that when running in the container. And in many cases, or actually composition of the containers. And in many cases, you also have a bunch of systems that developers need to integrate that you can't even put in the containers. Some like legacy system or some systems that require special hardware, right? So in those cases, you need to think about how you're going to do that. So one of the ways dealt with that problem, we built another tool called BigRig that allows you to define different environment, different ways, kind of like like Docker Compose file, but for environments. So you can, each environment is kind of like Docker Compose on its own, right? And that file is committed with the source code of the artifact itself. So that way, the same code again kind of used in production and development environment, but the tool does it differently on the production development environment. So it kind of helps to bridge the gap. So all that stuff we needed to figure out before we actually went first time into production. But that made us very, very comfortable with the technology. So we thought that we figured out all of the kinks. We thought that we got it to the point that we can manage it. And we went into production. And our developers started to be very excited about that. Everybody started to invent new things, how to deal with this new technology. This is a very exciting time right now. Those technologies are still in flux. So there are a lot of inventions going on. So but then this is what happens. Like that. So you're starting to get to the point, which is we always wanted to build microservices. Wanted to make services so simple and easy to manage and control, and full service for each function. So we started to go developers crazy with the services. We're starting to get like thousands, millions of them all over the place. So I like to say it like, why bad things happen to good people, right? So that you can see the graph from Netflix. This is the graph from Twitter, and there are a bunch of found. So all the companies that are really, really embracing those services, they kind of end up there. And you need to make some sense out of that. So you usually, again, kind of fall into the state. If you're changing something, do you really know what you're actually changing in this environment? So we fall back into, let's start guarding our environment. But this is not really what we wanted. We wanted to move away from the environment. So to deal with that, we built another thing to control, actually make sense out of our changes in the environments. So you need to have a good change management. And ideally, it's not the system that has a very human-centric or human-involved process for approvals, but the systems that keep a very, very good track of what is happening in each environment, in each data center. You need to know who changed what, when, what versions has been changed, what is deployed, what is deploying right now, what is changing right now. So it's becoming very, very important to keep track of that. So this is a system like Janos, for example. It has a built-in mechanism that, since it knows the dependencies of the services, it can make sure that the services that depend on each other, they will not be deployed at the same time. Because if you have a lot of different changes at the same time, to like services that depend on each other, you don't. If the failure is happening, you don't know where it came from. Did it come from the new deployment? Did it come from the new version of the code, like service A or service B? So you need to pay a little bit more attention how you're going to manage all this change. So this is also open source, called like part of the accordance system. But then you need also to keep a track of all those dependencies of the services in order to become smarter about the change and how to control the change. So going back to my point, as I mentioned, like if each service, each artifact has a declaration of what it needs to be successful in the production, then the system, like for example, accordance dependency management, can help you to keep track of all those dependencies. And you can navigate, or anyone in your organization can navigate those dependencies and make sense and see what depends on what, and if a change or maintenance request is happening, what items in the environment they can touch or change at any moment of time. So after that we actually need to know about the dependencies, we start to run the problem how we're going to find those dependencies. So going back to our original point where we had more or less static data center, we learned how to deal with that more or less by putting a lot of DNS records all over the place. So our service A that needs service B has an entry in their DNS resolution to say that service B is located at b.company.com and b.company.com resolves to that IP. So that's how they can find each other. It resolves to not to service directly to a load balancer. But when you're starting to have like thousands of services, that system doesn't really work well. Specifically when you have composition of the containers. When you're starting to have a composition of the containers, that really doesn't work. So when we started to move to microservices, we actually started to move more into service discovery, move the services to service discovery to move away from Docker linking and Docker composition. But then the service discovery actually needs to know when it connects the services together, it needs to know about the state of the application, if the application is running. And this is where we start to run into my previous point, as I mentioned. Or the system needs to know very well if the application, after it's starting in that composition of the containers, is it actually healthy? Can it receive any traffic? And that's becoming very not trivial problem. So when you're building your services in the containers, keep in mind that the container starts much faster than the VM. So when the Docker says that the container is running, your application may not yet running. So with the VM, when we were using virtualization, it takes more time to start VM, and the application more or less catches by the time when the VM is ready, application may have enough time to stabilize. But then Docker container is becoming acute, the difference between when the container is actually launched, or Docker says that I've started the container, and the application actually keeps up with the start process. And by the way, you can stop me anytime if you have any questions. So make sure that when you're building your orchestration or using any orchestration, that orchestration actually knows how to deal with that time. So put some stagger in place, or put some like time from the moment when you start the container or you run. Or in one of our tools that we've implemented, when the tool was starting those containers and composing them together, it had a check information in that configuration file to say what it needs to pass before it actually launches the next container. So in this case, it helped us to make sure when we start applications actually running. So that brings me to the next topic of monitoring. This is becoming very important. Before that, we knew that monitoring is important and alerting. But now when we start to have way more containers, way more application services, it's becoming even more important because we need to make sense out of everything that was launching. So we learned very quickly that I need to start thinking about composite SLA metrics. Do not monitor the app and the container itself, but do not monitor the application in the container. Monitor the health of the whole application or service across multiple containers. So, as the story says, you need to smell the cheese as often as you can to know when it's good or not. If it's not good, just kill it and start a new one. It's much. But we started to run very quickly to the problem that the modern monitoring tools, they don't know how to reason about the containers. Every tool more understand about the container, that there's multiple zones contain environments, contains machines, virtual machines, Docker containers, and so on. But in reality, that doesn't really work. And specifically when we start to have multi-region, multi-data center applications, like simple examples like Cassandra, Hadoop, when they spanning across multiple servers, the fact that it's failing in one data center doesn't mean that the whole application is down. It means that maybe it automatically needs to provision that we need to raise like whole hell of alarms and start saying that we're down. It's not really. So think a lot how to configure those monitoring tools. And specifically, if you're using anywhere relies on the server names, just stop doing that. You will not possibly keep up with that because there are like thousands of containers and they're constantly coming up and down. So those tools, they cannot keep up with this change. And specifically in this case, I just given a small example here. So what is happening if the machine, a virtual machine, is like misbehaving, then like everything inside misbehaving, or if there's just the storage fails, maybe a bunch of the containers starts to misbehave. So it's very important after you detect it and monitor the application and you identify that it's failed, you need to know how to deal with the failure. In many cases, then the failure, it means just you need to shut it down. But when you're shutting down, you also need to remember that it's not a single container, it's the whole composition of the containers. And in many cases, the composition of containers, some of the containers, they have to be running in order for application to work. And some containers may not be running for application to work. I'll give you an example. What if you have application that writes into a log partition and the log shipping container died? The application continues to work, but one of the operational containers died. So in this case, the system can just restart the container and declare the whole instance to be dead. So orchestration tools not always understand that difference, right? So we needed to write a lot of logic to deal with that. And you also need to remember you can just kill and dispose of them. Some containers may not, because it may contain some information that you still need. Maybe like for troubleshooting, or maybe some data that you need to ship out of those containers. So when you shutting down containers, keep that in mind. So I'll very briefly touch about that. So please do not put your production data in containers, because the containers disappear very quickly and you will lose all your data. So think about either mounting the machine storage or more resilient storage to your containers. If you need to keep, let's say, database, you can run the database process inside the container, but it's like the database itself do not keep inside the containers. There's a very interesting development. I'm monitoring what's happening inside Flocker. They have some mechanism to move the container from one place to another if it fails on one machine. But just keep in mind that the size of the container, size of the data inside the container can be so big that may not have enough time to ship it over. Right? So just keep in mind. So log management. This is one of those pieces of data that you may keep. And today we encourage to write a lot of logs. This is great. But also think about this. If you have thousands of containers, the amount of data that you generate in logs become just, in many cases, prohibitively large. So put mechanisms that allow you to control how much data and when the data is generated. But today, one of the suggestions is to write your logs into Docker, and then you can use Docker logs to look at what's happening. But remember that data stays inside the container. And it's actually always accumulates. It always will start to show you a log from the beginning, and not from the place where you're running right now. So we learned that we just don't write to standard output. We write always to the log file, and we mount either like another Docker container to keep those logs, or we mount machine storage. And ship this data very, very quickly from the containers, because again, as I mentioned, the containers disappear very, very quickly. So that was our starting point to the Docker. And we learned that we needed to be very, very quick to adopt those new findings that we found out. And that brings us to the topic of Mesos. So after we've been building all those tools to manage and orchestrate those containers, Mesos shows up and helps us very, very quickly to make some sense and even simplify our orchestration. So Mesos became very quickly a top level Apache project. It allowed us to, and I'm talking for the moment on the inside data center, allowed us very efficiently use our servers. But then we also learned it has also a great benefit to run it inside Amazon or any other cloud, because it allows us very, very quickly spin up new servers, spin up new containers and shut them down. So for short running processes and tasks and batch jobs, it's great. So you can very, very, very optimize there. So I'll do a couple of shout outs to different frameworks. So we use Marathon containers, and it's great because if it dies in one place, it pops up in another place. It was great. Kronos was awesome to run batch job and like processing jobs, but we ran very, very quickly to the point that we needed to connect queues of jobs to those batch processing, and that functionality is missing in Mesos. So we've wrote a couple of other our extensions, which is not open source yet, but maybe soon, that allowed us to connect the queues to Mesos scheduler. So Singularity from HubSpot and Aurora from Twitter, they kind of help us to solve that, but we failed miserably to start them on our own data centers because they were not mature yet. But we continue to keep in mind to check them once in a while, and we hear good things that are coming. But one of the things that really impressed me is what like new development from Netflix called Mantis. It has Fenzo as distributed scheduler and Scryer as predictive auto-scaling. So they're building it to run at Amazon. Really, really exciting stuff happening. So pay attention. So we learned very, very well that Mesos helped us to manage Docker container both on public and the private cloud. We were very excited when Mesos started to support Docker out of the box. So Mesos Docker, it just simplified our life very, very much. But there are a lot of missing still features in Mesos. Multi-region management, persistent volumes. It still doesn't know how to manage those composite containers. Missing REST API, so I will not go there too much, but it's still young technology. And if you're thinking about that, just keep in mind its limitations. So change happens very quickly, and they're constantly moving cheese. The technology is constantly changing, so just stay on top of the change. It's a very, very exciting time right now. So a couple new things that what we're looking at was we really paying a lot of attention to development of Kubernetes. It's still a little bit early. We're still missing a lot of, as I mentioned, like the linking of the containers. It didn't work across the machines. I just heard today from Jerome that there is new Docker that's supposed to help us, and we're excited. Maybe like we'll check it out very quickly. Lambda architecture is very, very promising, but we still ask questions. If we're running on-prem, what would be an alternative? So we kind of looked at Storm, and we're using Storm very, very heavily, but we would like to see something like Lambda, some alternative running on private data centers. Tracking is, we very heavily working on that. We need to make sure that when the failure is happening, as I mentioned, like to reason to make sure that our monitoring and alerting tools, they know how to reason and understand those dependencies and those. And just I'll do one last shout out. When you have all those dependencies of the services and you're having a lot of them, you very, very quickly start to ask a question, how's the data flow through the system? You're starting totally very, very quickly to lose the tracking system. And I'm very excited looking at a lot of different companies, they building tools around this, open source yet. So Salp from Netflix, they kind of can build a graph of data flow through services, and Hello, they build something of their own that even builds the time series diagram. I'm building right now part of Accordance that will use Argus as open source tools to kind of like automatically detect those dependencies. So that's exciting. So I have to do credits, and if you have any questions, you can always find me. As again, I mentioned that I'm looking to help other companies, and really excited to hear about your challenges that you have in your environments and your systems, and to hear about how you solve them. That would be great to share. Thank you very much.
So yeah, I think we have time for one or two questions. We're a little over, but that's okay. Anybody has any burning questions for Igor? Putting you on the spot there right now. It's like, okay, so we have one more session to go. Basically, if you haven't voted yet, go to the open spaces board in something like 3 or 4 minutes. We're going to pick the 4 last topics. We'll have a short open spaces session, same rooms as before. And then, just to keep everybody here, we're going to hand out the beer tickets in this room at about 5 o'clock. Thank you.
No, I did not get the screen, but I did get when some
So
of
you
that.
want me to slide
like, you know, now, if you guys do the composition, or just if you can send it to us, we can post it. But I suspect you already have it posted somewhere. Yeah, I'm usually putting it. So you can send us a link, and we'll be very happy to place it on online. But the sound is good. Awesome. Which is, we're very happy that these things are around.
Hi, I'm Steven. I'm from HubSpot.
I see from HubSpot.
It actually doesn't have to be now, but I'd love to on when you were trying to get Singularity up and running for, pure feedback's sake. We've been doing a lot of work on it, so I'd love to, hear feedback on how it is to users outside of HubSpot. So, yeah, I don't know if you had a question first. Go ahead. But
no, mine's going to.
You guys work together? No, I talked to you earlier. But
no, my question. Like, how do you get secrets into containers?
Yeah, let's get on like that.
Cool.
One of the ways that I didn't do the containers, but like I suspect just check it in the included way.
Yeah.
It's very sort of simple and easy to.
Yeah. Well, so this is more for like there was an earlier breakout session of how you do this, and basically, I don't think anybody has a good way of like, well, these certificates we need to get onto these things, and based on which environment they're in, it's going to be different certificates, like your dev versus prod. Yeah. Okay.
Like one of the things for